Good morning, sir. First, sir, good evening for you because you are in the USA. We will start at 10 exactly 10. Sir, if you can unmute yourself.
Okay.
Yes,
Yes. Can you hear me okay now?
yes, sir. Yes, sir.
Perfect. How are you?
Fine, sir.
It's been a long time. Yeah.
Yes, sir. Almost 2.5 years.
Right. Right. I see you are in your lab or university. Are you doing classes in person?
Yes, sir.
Okay. Okay. I'm also going to join in from my iPad. Let's see if that works. Let's try this out.
Yes, sir.
Okay. I'm going to try and share my screen from the iPad. I want to mute myself here. So it says there is an error. I cannot share my screen. Let me try this again.
Sir, if you have Google Meet application in your iPad, then you may share your screen.
I don't have the application. I'm just using the browser. That's not going to work.
Sir, I don't think so because in the Google Meet app only you have that option to share your screen. I mean for iPad only. You have
Okay,
to.
let me see if I can quickly install that.
Yes, sir.
So tell me a little bit more about this course.
So it is a TQIP sponsored short-term course, and we are asked to organize it for at least 10 lectures.
Okay.
So I chose this topic because it is the favorite topic. Means Madhuri sir is working on this. That's why I chose this topic.
Great. Okay. I have the app now, and
Yes, sir.
then uh, what do I do? Okay. Let's see. I think I've joined. Let's see if I can share my screen. Okay, seems to be working. Okay, great. I think this is looking good. It's set up. All right. Are you able to still hear me? I changed over to my
Yes,
headset.
yes, sir. Yes, sir.
Okay, great. So this is a 10-day course, and you'll have 10 people come and give some lectures.
No, sir. 5 day course. We have two
Okay.
sessions. So
Okay.
10 lectures total.
Okay. And can you tell me a little bit about the students or the people who are taking this class?
Sir, so most of the students are undergraduate level across India,
Great.
and we have few PhD students and few lecturers and assistant professors from different universities.
Okay. So what happens after they're done with the course? Is there some sort of an exam or uh,
Uh, no,
evaluation or something?
no, sir. There is no evaluation. They will just attend this course, and they will be given a certificate of just attending the course.
Okay, great. All right, so I'm all set up. So whenever you want to start, you can go ahead. I think we have another 5 minutes.
Yes, sir.
And you want me to, by the way, you can call me Shayan. You don't have to call me sir. And this is planned for like, what, couple of hours, hour and a half?
Yes, sir. So it's fine. Means it's up to you. You can take as much time you want.
That's a very dangerous thing. We professors can keep talking for hours. So, but this is 10 o'clock, right? So we
Yes,
probably
sir.
want to stop at around noon. So I'll try to stay within that. Do give me, a reminder of the time and so forth. So at least when we are halfway through, maybe you can give me a reminder. We'll probably take a break sometime in the middle.
Okay, sir. Okay. No issue. So very good morning to all the participants, and good evening to our speaker of the day, Professor Sayan Mitra. So it is a great pleasure for me to introduce the speaker of this session, Professor Sayan Mitra. Professor Sayan Mitra is a professor of electrical and computer engineering at the University of Illinois at Urbana-Champaign. His research interests are in thermal verification, distributed computing, and cyber physical systems. He holds a PhD from MIT, USA. Uh, he was a postdoctoral fellow at the Center for Mathematics of Information of Caltech, uh, and and held a visiting faculty position at Oxford University. Uh, and he has published books and many research papers in reputed international and national journals and conferences. So he is also an active reviewer of many reputed international and national journals. Uh, he has a membership of IEEE, ACM, HKN, etc. So, so now I request Professor Sain Mitra sir to kindly join us for a great session. So it's over to you, sir. Thank you.
Okay, great. Thank you very much for giving me this opportunity to speak with you. It's a pleasure. It's something very new for me. Let me check whether you're still able to hear me okay or not before I get started.
Yes, sir, we are able to hear you. No
Okay,
issue.
and some of you in the audience seems to have your microphone on. So if you can keep it mute, that will be great. Of course, at any time, feel free to interrupt and ask questions. Okay, these long
Yes,
lectures can get pretty drab and boring, and no question is a silly question. So feel free to just interrupt and ask questions. I have prepared a talk on verifying autonomous systems today. But I could talk about various different things which are related to this subject. I could talk about, for example, education and research in the US very broadly. I've been at this university for 10 years and in the US for more than 15 years now. Some of you might be interested in doing research abroad, so I could talk about that. I could talk about other related topics also. So please feel free to interrupt, and having questions answered makes these sessions much more lively and interesting. Okay, so the topic for today is autonomous systems. I'm showing this video just as a way of introducing the topic. Maybe over this screen share, the video is a little bit choppy, but you can sort of get the sense. What this video is showing is a bunch of cars and people and bicycles, motorbikes going through an intersection at a very fast speed. Okay, almost like a insanely difficult speed. And India, sometimes you will see these things happen with human drivers, most of the time safely, but sometimes things become unsafe. But in the US or in rest of the world, navigating safely through traffic very quickly is a very challenging problem. And uh, this video is like actually a fake video. It's not the cars are not driving autonomously here. It's artists' rendition of what autonomous driving would look like if you had perfectly autonomous cars driving through a city intersection. Okay, so why are we so excited about autonomous cars? There are lots of advantages. You can have delivery of goods without involving people. That can be very efficient. Um, in cities, cars take up a lot of parking space. So if you didn't have to park the cars, then you could have more parks and space to walk in the cities. That could make the cities more green and more livable. And also, safety is a big topic, right? So, in the US alone, 35,000 people die every year in road accidents. That's the size of a small city, and the hope is once you have autonomous cars, then it's the transportation will become a lot safer. That's not obvious, but a lot of companies are working on this. This slide shows some of the top 200 or so Silicon Valley startups that are trying to build some parts of the autonomous car. But you also hear about some of the hype, and now the reality is starting to sink in, and people are realizing that building autonomous cars is not going to be that easy. And you may have seen some newspaper articles, reporting on fatal accidents and even sort of trivial cases where a pedestrian or a bicyclist is crossing the road, the car is not able to detect it in time, and leads to accidents, right? So there's a lot of excitement, hope about getting autonomous systems working, cars, drones, ambulances, but it's turning out to be much harder than what people imagined even 10 years ago. So before launching onto the technical part of the talk today, let me tell you about another race that was happening 100 years ago to build another type of engineering system that was tantalizingly close. It seemed like we were almost about to solve the problem, but it turned out that some key ideas were missing. Can someone guess what was happening 100 years ago? What kind of engineering system we were about to build that changed the world? Any guesses?
No, sir. No, no idea.
Let's see. Maybe some of the others in the audience.
Pavan,
Making things easy, just comfort.
Sorry, I didn't get that, Pavan. So making things what again?
Easy.
Easy. Uh, it's let me give you a hint. It's also related to transportation.
It's a
Uh,
plane.
what was that again?
It's an aircraft.
Airplanes. Yes, exactly. So in fact, there's an interesting article that appeared in 1901, which is a little more than 100 years ago, in the New York Times, famous newspaper, which says, you know, all these people are trying to build airplanes of different types, but who knows? It might take 50 years. We don't seem to be anywhere close to doing it. Okay. So this next video, I think, shows some of the crazy ideas people were having at that time for building airplanes. Okay, so you may have seen these types of videos before. And one of the things to note is people were clueless about what was the problem, like what was the hard problem to solve, right? So some people thought just getting the plane off the ground is the hard problem. So they were building these machines to just launch the plane. Okay. Then some people thought the propulsion was the problem. So they try to play around with different kinds of rockets to see if they can push the plane hard very fast. And, you know, some silly things with people trying to put rockets on their backs. Um, then people thought, okay, building the wing of the plane is going to be the problem, right? Because birds have wings, planes got to have wings. How do we build big wings? Um, and then, engines. There were lots of experiments with building bigger and more powerful propellers and engines. Okay. So you see some of these examples also where just the engine is so big, keeping it structurally together itself was another problem. All right, so you get the point, right? So there were lots of people trying different things, sort of like what's happening in Silicon Valley now. Many companies trying to build autonomous cars with different approaches, but something seems to be missing. Okay. Uh, then you guys know like how the problem got solved, right? The Wright brothers in 1902, just 1 year after that article appeared in New York Times, actually demonstrated successful controlled flight for the first time. Right? Now, how many of you know what was the actual problem that they solved? Okay, so this is the picture of their airplane in Kitty Hawk, right? Kitty Hawk is the place in sort of the coast of the US where they were experimenting with their planes, right? But do you know what was the actual problem that they were working on? Let's see if there are any guesses here. Yeah, I'm going to ask you lots of questions. In fact, there's going to be a quiz sometime in the middle of this lecture, okay? Just to keep you all engaged and awake. The question I'm asking right now is, what was precise problem that the Wright brothers solved when they flew their plane in Kitty Hawk? Okay, maybe I'll give you some options. Oh, aerodynamics. Mr. Sharma, could you be more precise? What precise problem in aerodynamics was it? Oh, maybe I should be looking at the chat. I'm not able to see the chat. Uh, yeah, oh, aerodynamics was definitely part of it, but what specific problem in aerodynamics? Let me answer. They figured out how to control the plane. Okay, so it was not about propulsion. It was not about getting the aircraft up in the air. It was about how to control the plane. In fact, people knew how to control the plane to go up and down, right? Pitching up and down was well understood at that time. What they were figuring out is how to make the plane turn. And that was a complicated thing that they had to study. They, in fact, looked at the birds for the longest time to see how birds manage to turn, and finally figured out this is a combination of this rudder that you see here. This is the rudder of the plane, and then they had some flaps also in the front. Together with the rudder and the flap, they were able to control the plane. Anyway, so why am I telling you about all this? We feel that for autonomous systems also, there are some key pieces of the puzzle that are missing. Okay, we need to solve some problems that we are not looking at today. And this brings us to our topic, which is verification. Okay, so very quickly, what is an autonomous system? It could be cars or drones. It could be any kind of medical robot. But at a very high level, there are three pieces to an autonomous system. There are these sensors, right? So LiDARs and cameras and GPS. Ultimately, with all these sensors, oops, slides are moving too far ahead. With all these sensors, the system creates a virtual representation of the world. And that virtual representation is used by the decision and control part of the system. So this is where you have algorithms. And that decision and control algorithm then decides how to move the vehicle or fly the drones, right? So it sends the steering actuation commands. So those are the three high-level pieces. Okay, so what's some of the missing problems here? Why are we finding it so difficult to work with autonomous system? There are many issues, but one topic that we will focus on today is this issue of reliability and safety. Okay, and people have looked at different ways of calculating how to make such systems more reliable. And a rough calculation that a lot of people accept now shows that to get the kind of reliability that we have come to expect from, let's say, aircraft systems, vehicles will have to drive something like 30 million miles. Okay, 30 billion miles of testing. Okay, I just saw a message which says my voice is echoing. Is that still a problem, or?
Sir, no problem, sir. I can hear you clearly.
I'm thinking whether I should turn something off here to prevent. Say that again.
It is okay.
Okay. Thank you. All right. So one of the problems is reliability, and the challenge is that the bad things can happen very, very rarely. Okay. So building a system which works 80% of the time is relatively easy. You can get to that point pretty quickly. But then getting to the point where it works 99.9% of the time, that can be extremely challenging. In fact, we may not even have the tools to get to that point. That's where this 30 billion mile kind of number comes into the picture. Okay, so how do you check for reliability? How do you make systems more reliable? Well, one approach is testing, right? So if you have a system like autonomous car or any kind of autonomous system, you can run many different tests on it. So this picture shows that, this blue car here is the autonomous car, and it is driving around several other cars, and it is going along different paths. And you can run one test in which the cars will move along the lines shown here, and then you can run another test, and you can generate all these different tests, right? Which will develop all these different paths, and you can check along any of these paths if the system becomes unsafe or not. But the problem is there are many such possible behaviors of the cars. There are uncountably many behaviors of the car. So you couldn't just run a finite number of tests to say, I'm done, to say that, okay, this is now a safe system. And these different paths come from all these sources of uncertainty, like road friction and failures and behaviors of the drivers, like the drivers could be distracted and so forth. So an alternative approach that is promising is what we call verification, formal verification. And this is what the rest of this presentation is about. So let me tell you what the verification problem is. So ultimately, we are looking at this piece over here, which is a formal verification tool or algorithm. And what this algorithm takes as input are two pieces. It takes a system model, which I'm calling A here, and it takes a requirement. Okay, requirement basically defines what the behaviors of the system can or cannot do. Okay, and with these two inputs, then the verification algorithm can produce one of two kinds of outputs. Either it says all behaviors of A satisfy the requirement. So that's a nice outcome. In that case, we are done. And how does it do that? Well, instead of computing individual paths, maybe the verification algorithm will compute all possible paths, as you see in the animation over here. And a second possible outcome of this verification algorithm could be that it finds a bug. Okay, in that case, it will show a particular behavior of the system, like the animation that I just showed, where the cars actually collide. Okay, so let me repeat this. So formal verification algorithm takes two inputs, the system model and the requirements, and either it produces a proof which shows that all behaviors meet the requirement. Often this is done by what is called reachability analysis, which we will talk about in some more detail, which covers all the possible paths or behaviors of the system. Alternatively, it can also find a counterexample behavior which shows a particular behavior of the system, which is a bug, which shows how the requirement is violated. Okay. Now, why is this useful? Why do we care? Well, if you get a proof like this one over here, then you can use that proof to certify the system. So you can show it to the federal agencies which are responsible for safety certification as an artifact which shows that, look, I have developed a rigorous analysis of my system, and this is why the system is safe. Okay, so this becomes like a legally useful document. On the other hand, if you find a bug, that is also useful, because then you can go back to the designers and say, hey, look, there is a behavior that violates the system. Now, can you fix the code? Or can you change the assumptions under which the system is supposed to work? Okay. All right. Any questions at this point? hopefully, I have motivated the verification problem in the context of autonomous and cyber physical systems. I haven't taken the time to define cyber physical systems. And I've defined what the verification problem is.
So it is clear up to now. It is clear.
Okay, great. Okay, now let me spend a little bit of time talking about what some of the. Okay, so here is the plan for the lecture. Let me go back here a little bit. So what we will do is talk about some of the technical challenges that come up in verification. Then I'll talk about a particular approach for solving this verification problem using execution data. It's called data-driven verification. And I'll talk about some applications of that, some examples. And that would take us to sort of the halfway point of this talk. Over here, we can discuss some open problems, maybe take some more questions. And that's where we will have a quiz. And if we are short on time, we can even stop there, okay, rather than rushing through more material. And if there is still time and energy, then we can talk about learning-based verification, more applications. This is an interesting application in the F-16 aircraft, a real-world application of formal verification in an autonomous system. And there's also applications of verification in synthesis, controller synthesis, which are pretty interesting. So I have just a few slides on that. We could talk about that. And then there are more sort of open problems to talk about in the end. All right. Does that plan sound good?
Yes, sir. Yes.
Great. All right. So what are some of the technical challenges for verification? Let's go back to this example that we were talking about. So this blue car is an autonomous car which has some advanced features, like it can do adaptive cruise control, it can maybe even pass other cars, it can have autonomous braking if there is going to be a collision. Okay. So first of all, if you start from the lowest level, there is a description of the car's physics. Okay. Like the mechanics of the car, how the car is moving on the road. Now here I've written down a nonlinear differential equation, which is a very basic model of the car. This is called the Dubin's car model of vehicles, extremely simple. The velocity of the car, V, changes according to the acceleration. This is like Newton's laws of motion. The X position of the car changes according to V of cosine of the heading angle, and so on and so forth. This model, for example, does not worry about tire friction and suspension and distance between wheelbases, differential braking, any of those things. It's an extremely simple model. But even for the more complicated models, you can write down, in some cases, some sort of a differential equation, or maybe you write down a Simulink model to describe the physics of the car. Okay, so that's the starting point. So this is the more general form. Most of the time, we'll just write down this general differential equation, which is saying the state of the vehicle is X, which can include all kinds of things like position, velocity, acceleration, moment of inertia, fuel, all of that. And the right-hand side is the physical law captured in this single function F, and U is the input. In the case of a car, the input is going to be the steering, throttle, and the brake. In the case of the drone, it might be the throttle inputs to the 4 propellers, and so on and so forth. Okay. By the way, if you're coming from the computer science background, this differential equation might look a little bit unfamiliar, and you might be more comfortable with this discrete time type of model, xt plus 1 equals fxt ut. Most of the things that I'm going to talk about today will hold with some small modifications for the discrete time models as well. Okay, it's just that the continuous time description is more sort of standard, and I'm just going to stick to that. But going from the continuous time to the discrete time is not a big leap. Sort of most of the mathematics actually carries over. So X here is a vector of what we call state variables, the states of the vehicle, position, velocity, etc. And U is the input, right? In this case, the steering and the acceleration inputs. So immediately what you see is what we're dealing with is a nonlinear system. Yeah. In fact, we are working with a nonlinear differential equation. And generally speaking, nonlinear ODEs don't have closed form solutions. You can have numerical solutions, but you can't write down closed form solutions. Okay, so that's going to be a challenge. Now let's take a step further. The physics of the car alone is not going to be enough to reason about the full autonomous system, right? So we have to put the physics together with the software which is making all the decisions, right? So for example, in this animation that I'm showing you here, the car is trying to do a overtake maneuver. And this overtake is going to be controlled by the software. And if you look inside the software, it might look something like this state diagram that I've drawn on the right-hand side of this slide. The car starts out cruising with a constant speed. Then it did this left motion, right? So it went left to go to the left lane. Then it sped up to do the overtake, crossed the blue car. Then it came back. So it then merged back on the right lane, and then it slowed down, right? So there's a sequence of things that the car is doing in this particular maneuver. And that sequence will be described by some sort of software program transition system, okay? And in each of these different modes, left turn, right turn, speed up, the physics is slightly different, right? Because the inputs are different. The car is going to behave slightly differently. So, and yeah, the softwares can be quite complicated here. There are just 4 states that I've drawn, but generally there could be dozens or even hundreds of different states that the software has to go through. So when you put those things together, what you have is this type of a model. There is the physics and the software sort of running in closed loop. And this gives rise to what we call a hybrid automaton or a hybrid system. Hybrid, the term is coming from the combination of physics and software or computer science and control theory, basically. So this is what it would look like. You have these different modes. This is the software state of the system. And in each of these modes, the car is moving according to some physical law. Okay. Now, this is a very simple example, but you can think of this applying to all kinds of systems. You know, a robot moving, right? That will have this type of a breakup where sometimes it is, turning on one foot, at other times it's turning on the other foot. So those would be 2 different modes of that robot. If it's a drone that is sort of flying, maybe sometimes it's diving, sometimes it's flying straight, sometimes it's turning. All of these things are going to be the different modes of that drone. So this is the second challenge. This combination of physics and software makes the system even more complicated. So here is an interesting thing to know. Interaction between computation and physics can lead to unexpected behaviors. Okay, so think of this example. So let's say you have 2 different modes of the system, right? The orange mode and the blue mode, okay? And look at these modes. In each of these modes, the trajectories are all converging to the center, right? So each of these modes are what is called asymptotically stable. They're nice and convergent. Now, it's possible that you switch between these 2 modes in a way that the overall system is actually unstable, meaning the trajectory is going to fly outwards. Can you see this? So look at this black lines that I'm drawing here. So the black lines are switching between the orange lines and the blue lines. However, even though the orange and the blue spirals are going inwards, the black line is flying outwards. So the black trajectory makes the system unstable. Okay. So these types of things are very common in hybrid systems where you put together a few different modes which are individually stable, but by switching between these modes, the overall system becomes unstable. Okay, that's why we need to worry about the combination of things. You can't just reason about the individual modes and say I'm done. You have to worry about how things are interacting with each other. So that's the second source of why this problem is hard. All right. So with that as sort of motivation, we have talked about some of the verification challenges. Now let's talk about the good news. So I'm going to give you some approaches for solving this reachability problem. Okay. So let's first define this reachability problem or the verification problem at an abstract level. So consider for now an autonomous system model. So you have a differential equation dx dt equals fx, no inputs, just to keep the story simple. A single trajectory of the system starting from an initial condition x naught is drawn by this red line here, and we denote it as x of t, right? The solution of the system at time t. So that's sort of what it looks like for a car. Now, what we are trying to say is we want to check whether starting from all the initial conditions, all the initial states over here, whether the car is safe or not. In this case, safe means it doesn't hit the red rectangle. Okay, that's the canonical safety verification problem. So this unsafe set or the bad set is denoted by U over here. And we want to check whether all the trajectories of the car starting from this set, whether they all remain safe or whether it is possible for some trajectory to go and hit the unsafe set, right? So this is the problem we are trying to solve. So this thing actually has a name. If you look at the union of all the trajectories of the system or all the solutions of the system, that's called the reachable set. Okay, that's a very important concept. That's sort of a central concept in verification, is this notion of reachable set. Okay. Just a second here. Right. So, so another way of describing this verification problem is to say that we want to check whether the intersection between the reachable set here with the unsafe set is empty or not. So this is what we are trying to check. The union of all the trajectories is this pink set, and we want to check whether this intersection between the pink set and the red set, whether this is really empty or not. Okay. So this is called the reachability problem, and this is a very hard problem. And let me just tell you why this comes up everywhere. So we already saw this example in the context of cars. In the case of drones, you can use reachability for real-time planning. There's supposed to be an animation here. Let's see if it's playing or not. Okay, so for some reason this animation is not playing. Doesn't matter, but you can sort of make out what's going on here. There are a bunch of drones, and each of these drones are computing some reachable sets over here to check whether they're going to collide with each other or with the walls of the building or not. And if you can do this kind of reachability analysis very fast, then you can use it for planning. There's reachability analysis also used for spacecraft problems when two satellites have to dock with each other. then you can compute these reachable sets to check whether this docking is going to be safe or whether they're coming in too fast or not. Those are sort of obvious applications, but increasingly reachability is also used in somewhat newer domains where the models are very complex. For example, there's applications of reachability in uh, checking whether cars are going to collide with pedestrians or not, right? So if you have a model of the pedestrian uh, and you can sort of predict how the pedestrians are going to move, then you can compute the reachable states of the pedestrian and use that to check collisions with vehicles. Okay, and here is another one that is quite novel. So when people try to predict the path of storms, like tropical storms, it's also another kind of reachability analysis. So in fact, the cone of the storm that you see here is precisely the reachable set that we just defined. Of course, the weather model is much more complicated. It's not like a differential equation that I showed you. It's probably a partial differential equation with lots of different inputs coming from different measurements. But the core computation is still a reachability analysis computation to check which part of the continent or the country this storm is going to reach, right? So this is a ubiquitous problem in verification, and it's obviously also very important in autonomous systems. Okay, so I'm going to skip over this slide. It talks about the history of reachability analysis. There's been a lot of important work that has happened over the last 30 years, ideas coming from control theory and computer science, intuitions coming from stability analysis in control theory, Hamilton-Jacobi equations for characterizing the reachable sets, and also ideas from computer science, in particular data structures like zonotopes and support functions. These types of things have made reachability analysis sort of feasible. Let me just summarize this by saying that for linear systems, reachability analysis for up to thousands of dimensional systems is feasible today. In some cases, even tens of thousands of dimensional systems. Okay, and when I say dimensions of the system, it's really going back to this this vector, right? So we talked about the model here, x dot equals to fx. So think of x as a 1,000 or 10,000 dimensional vector, and the function f is a 10,000 by 10,000 matrix, right? Because it's a linear system, and you're trying to compute the reachable set, like this orange set that I showed here, and such problems are now solvable. Okay, fairly recent, clever algorithms for the last 10 years make it possible. Okay, now for nonlinear systems, it's a whole other story. And that's what we want to get into now, right? Because you don't have explicit solutions, it's a much harder problem. And what I'm going to tell you are these data-driven approaches, which make the problem somewhat tractable. We are not yet at the level where we can solve it for 10,000 dimensions, but there's some promising new results. Okay, I've been talking for a while. Let's see if there are any questions in terms of the problem setup and what we are going to do next.
Is there any reachable set can be finite or it is infinite?
Yeah, that's a good question. The set itself is typically infinite because the state space is some subset of Rn, right? Subset of real numbers. So the number of states that are reachable is going to be uncountably infinite typically. But the set will be represented using something finite, like a finite union of rectangles or ellipsoids or things like that. So we will always work with some finite representation of this infinite object.
So suppose I will take example of a car, autonomous car. So in that case, uh, what can be the reachable set for a autonomous car?
Hang on to that. We'll get to an example in a moment, and I think it will become very clear.
Okay. Thank you.
In brief, the reachable set will tell you what are the positions and velocities of the car at different points in time.
Okay. Thank you, sir.
Instead of an individual position velocity, you will get a whole range of positions and velocities.
Thank you, sir.
Yeah, sure. Any other questions? Great, by the way, any question sort of is very reassuring to see that people are following. And if not, I can always go back. I'm in no rush to cover a number of topics. Yeah. All right, so let's talk about this reachability analysis question. And I'm going to talk about a particular algorithm now. The idea is pretty simple here to start with, but then it gets into some advanced math. Okay, so I want to just give you the intuition. And then, of course, if you are really excited by it, you can go read several papers. And if you are really, really excited by it, then you can even download the tool and start to play with it. You can create your own models and see how the tool actually implements these ideas. Okay. So the idea is the following. So let's say, you can generate individual simulations, right? So you have the differential equation that we wrote down, x dot equals to fx. And you have a solver for the differential equation, which generates numerical solutions for it. So you can generate an individual solution. So this red line that you see over here is a single solution that is generated by the solver. Say MATLAB will solve it for you with ODE int. That's a function in MATLAB that will generate a single solution for you. Okay. Now, suppose you could generalize that single solution to this orange set, which gives you what the neighboring solutions look like, right? So suppose you can sort of figure out how sensitive is the solution to changes in the initial condition. Then what you can do is you can start from the single solution and then sort of bloat it or increase its size, add a little ball around it to say, here is where all the solutions are going to live. Right? So for that, you need this critical piece of information. You need to know how sensitive is the solution to changes in the initial condition. Okay, so this notion of sensitivity is what we formalize with a mathematical definition. We call this the discrepancy function. So basically, it's a continuous function which upper bounds the distance between the trajectories as a function of the distance between the initial states and time. Okay, so at any time t, if you look at the distance between the trajectories, this is x1t and x2t. So the gap between them is upper bounded by this discrepancy function beta, which takes the initial distance between the two and the time at which we are trying to bound the gap, right? Okay, so if you have such a function, then you can do the thing that I was saying in the previous slide, right? So you can take an individual solution, x of t, and sort of add to that this beta function t, the add here meaning you can increase the size by beta. So a single point will become a circle like the circle shown here, where the radius of that circle will be the beta. And then you have computed the reachable set for the system, or at least at that time. Okay. Now, there is a second requirement here that also I'm going to skip over for now. It's very important for completeness of the kinds of algorithms that I'm going to talk about, and we can come back to this later on. But for now, let me skip over the second requirement for the discrepancy function. It has to do with the precision of the over approximation that we are going to get. Now, how can you get such a function beta? Does anyone have any hints or any ideas about how do we get such a beta? Okay, maybe this I should go on with this. This might not be so obvious. If you know the Lipschitz constant of this function f, right? So remember, f is the right-hand side of our differential equation. If you know the Lipschitz constant of s, what is the Lipschitz constant? This Lipschitz constant gives you a measure of continuity, right? So the change in f is upper bounded by L times the change in the argument, right? So if you have such a constant L, this is called the Lipschitz constant. Lot of functions are Lipschitz continuous, like sine x, cosine x. You can find Lipschitz constants are going to be upper bounded by 1 or 2. A lot of functions are not Lipschitz continuous, like x square or e to the x is not Lipschitz continuous, okay? But Lipschitz continuity is usually for differential equations like this. Lipschitz continuity of f is a very mild requirement. Most functions on the right-hand side will be Lipschitz continuous. Here, what we are saying is we want to know what that Lipschitz constant L is. Okay, all right. So if you have that, then immediately it follows from Grunwald's inequality. I'm not going to do the proof here. Using Grunwald's inequality, it follows that the distance between the trajectory is upper bounded by this exponential function. So this is the beta we are talking about, right? So this is initially the initial gap multiplied by this exponential thing, e to the LT. Okay, so that's a candidate beta. Okay, so we have a starting point to our solution, right? We have a trajectory and we have a candidate beta, so we can use that beta to compute the reachable sets of the system around that trajectory. But this beta is not very good. And you can sort of see why it's not a good beta. Let's say you have this trajectory. So it's the same picture again, x of t, starting from x naught. And if the beta is like this exponential function, and you do the trick that I was telling you, you're drawing this ball around this trajectory to compute the reachable set. But this ball is going to grow exponentially with time, right? E to the LT is an exponential function. So with time, this ball is going to be huge. As you can see here, it's become enormous. Okay, so that means this over approximation of the reachable set that you're computing is going to blow up with time, and that's not going to be super useful. Why not? Well, if you go back to our original story, what we are trying to do is, remember, ultimately we are trying to do this. We are trying to compute this over approximation and check whether there is some intersection between this reachable set and the unsafe set, right? But if this reachable set itself became enormous, right, the over approximation blows up, then there's always going to be an intersection, and it's not going to give us very useful information, okay? It's going to always say the system is unsafe. So this strategy gave us a beta, but this was not the most useful beta that we could work with. Is there a question? Okay. All right, so then we have to worry about what is a good beta, what is a good discrepancy function, and this slide sort of talks about some some idea, some characteristics we would want. Now I'm going to speed up a little bit and give you a sketch of the idea of how we get much more precise discrepancy functions. And this is where you can stop me and I can slow down, or I can also point you to the papers and you can find some of the details there. Okay. So the basic idea is we are going to use more detailed information about the model. Instead of using the Lipschitz constant, we will use the Jacobian of F. So recall that Jacobian is the matrix you get by taking the partial derivative of F relative to all the components of X. So for example, if you have a system like this is a nonlinear system. The Jacobian is this matrix. You can just see it's the derivative of each term in F relative to the U and the V, the two variables. Okay, so that's the definition of Jacobian. Now it turns out you can show that you can get another beta where instead of the Lipschitz constant over here, we have e to the ct, where c is the maximum eigenvalue of this quantity, which is the sum of the symmetric part of the Jacobian and the transpose of the Jacobian. Okay, so you compute the Jacobian of the system, look at the eigenvalues, which can be positive or negative, and the maximum eigenvalue gives you the C. Okay, so this is something you can compute, okay, and the proof you can read in the paper. But the point is, this C can in fact be pretty small, much smaller than the Lipschitz constant. In fact, it can also be negative sometimes. A negative C would mean that your Rich tubes are actually going to converge. Instead of blowing up exponentially, they can actually shrink with time, okay? Yeah, so this little example here shows that for a very simple system like this, the Jacobian is actually going to be -1, whereas the Lipschitz constant is still going to be positive, right? So it's quickly demonstrate that the Jacobian is going to give you a more precise reachable set. Okay, I'm going to skip over this. And there's one more trick here. Now, instead of working with the 2 norm of the system, so far we are talking about all this sensitivity, and whenever you talk about sensitivity and distance, you have to worry about some norms, and the natural norm is the Euclidean norm, and so far I've been talking about the Euclidean norm, but sometimes you want to work with a norm which is not the Euclidean norm. So you can do some coordinate transformations to make it much tighter. So the reachable set sort of, the sensitivity along the more sensitive directions is captured more precisely by this norm. Okay, so sort of putting it all together, this is how the algorithm works, right? So you have this initial set as before, and the algorithm starts by performing a reachability analysis with a single simulation. And if there is an intersection found, like over here, then it will go back and partition the initial set into smaller regions. For each of these smaller regions, it will compute the reachable sets separately. And if the reachable set over approximation turns out to be disconnected or disjoint from the unsafe set, then that part is taken out. It is done. It's proven to be safe. And this keeps happening until, as you see in the animation, it either finds a counterexample or it shows that all the parts of the reachable set are disjoint from the unsafe set. So that's the overall algorithm. Okay, this slide sort of repeats a little bit, so I'm going to skip this. And the theoretical guarantees you get from this are as follows. If the system is proven to be safe or unsafe, then indeed the original system is safe or unsafe, so it doesn't give wrong answers. And you also get this relative completeness guarantee, meaning if the system is sufficiently safe, meaning the distance between the actual reachable states and the unsafe set is big enough, then this algorithm will terminate. You will get an answer. It will not just keep running forever. Okay. Just 1 second. I see some messages in the chat, but I'm not able to reach the chat window. Okay, people are wishing everyone good morning. So good morning to you all who have joined late. Okay, let's see. I'm sort of now going over to talk about a couple of examples. So we've been doing some theory, math, algorithms. Maybe the examples will make things clearer. And then we'll do this little quiz. Okay, so let's see if that works. And then we'll talk about open problems. All right, so these ideas are built into a tool that we have developed in our group. It's called C2E2. There is that website, and you can download and use this tool. It has been used for many examples, and it's at this point, I think, quite usable and robust. So I'm going to just go forward with this example that I was showing you earlier. There are two cars. The blue car and the white car, and the white car is going to try and overtake the blue car following this algorithm. And so this is what C2E2 looks like. You would load a model. The model, like I showed pictures of earlier, but it has a program representation. Like, oops, what happened? XML like representation. I'm sorry, my PowerPoint somehow crashed. I'm going to relaunch it. Maybe it was not PowerPoint, it was the Google thing. Let's see. Okay. Screen share. All right, screen share is back. Yeah, so this is what the tool looks like. You would load a model, and that's what the model would look like in the tool. It has all the different modes and the differential equations. Then you would write down the requirement. In this case, the requirement, I think there's something wrong with the animation, so I'll skip that. The requirement basically says the two cars will have to be separate enough. And then you would press verify, and either, going back to this figure, either the tool will come back and say, yes, in this setting, the cars never collide, or it will come back with the counterexample behavior. I think I have some slides which show the output of the tool without going through the animation. Yes, so this is going back to the previous question about what does the reachable set really look like? And this figure shows that. On the right-hand side, there's this animation of what the cars are really doing. The white car is trying to overtake the blue car. But the more important thing is the plot on the left-hand side. The blue region is the reachable set of all the behaviors showing the separation between the cars, okay? And you see the separation starts out with something, then it grows and it keeps growing. Okay, so this is the over approximation that has happened. And you have some intuition of which part of the maneuver had what kind of separation. But at all times, the separation was more than the required separation, which is, some value like more than 0. So because this blue region is above 0, in this case, there is no collision of the cars. Okay. And the reachable set has information about other things also, like the velocities and the absolute position. But here, for the purpose of the safety check, all we care about is the relative position of the cars. Does that make sense? Yeah. And then if you change the settings of the car, for example, you change the algorithm a little bit of how the cars behave, or maybe change the initial condition of the velocities, then the tool will go and find counterexamples. So here, the cars actually do get too close to each other, right? So that's sort of a situation where the cars actually do collide, and the tool is able to discover that. There's a couple of other examples in the slides. Maybe I'll skip that. This is a challenge problem that came from Toyota. This was an engine control system. The models for engine control system are very complicated. These are very carefully protected trade secrets for car companies. And so they created a model, which is not the real model. It's sort of a toy version of the model for researchers to play with. So we tried our tools on these models, and we got reasonable results. So I think, so you can see the differential equations get pretty complicated pretty soon. Polynomial differential equations with lots of coefficients, but the tool is able to handle these types of things now. I think I'll skip over the details of this case study. Let's see if this quiz thing works. Okay, so I'm going to start it from this other thing. Any questions or any comments on how things are going so far? Too fast, too slow? After this quiz, and we discuss some of the maybe challenges and open problems, we can take a little break and then reconvene. How about that? Does that sound like a good plan, Dr. Behra?
Yes, sir. Yes, sir. It is fine.
Okay. Let's see if I can launch this quiz. All right. So I would like to share my screen from this other computer now. Share. Oh. Okay, it's asking me to give some permissions. Let's see if this works. Okay. All right. Okay, I think that's fine. Okay, so the way this is going to work is you all will have to go to a website. All right, let's see. I've never done this before in a setting like this, okay, with international audience and different time zones. But I think it's going to be fun. So let's try this, okay? I've done it in my classroom now with the pandemic. We are all teaching remotely, and we try various things to keep students engaged and get their attention and ask questions. Okay, so what you need to do is you have to go to this website, www.kahoot.it, okay, on any browser. It'll be great if we get a signal from the students that they're able to do it. Students or the participants, I should say, because I know there are some professors and some postdocs here as well. So pardon me if I sort of address everyone by students. So you need to go to this website, okay, www.kahoot.it, and then you have to type in this pin that is on my screen. You don't have to present or anything, okay? Don't present. Wait. The pin is 6248860. I'll repeat that, and I'll also broadcast my screen. I don't know why my broadcasting went away. Okay, so you should be able to see the screen and the pin number. I'll repeat the pin number 6248860. And when you log in, I think it will ask you to choose a nickname. Okay, so just choose some nickname. It doesn't matter. We are not going to grade this, or this is just for fun. But if it works, maybe next time we do it, we will actually use it to grade you or something like that. But now it's just for fun. So just choose some nickname. Okay, and you see some folks are joining in. So we have 8 players now. And there are going to be 4 questions, obviously multiple choice, easy questions. I'll wait for a few more minutes and then we can do this. In the meantime, let me see if I can. Okay.
I think आप mute हैं.
Sir, please unmute your mic. You are not audible.
Sir, kindly unmute. Yes. Yes, sir. Fine.
So you can't hear me?
No.
Okay.
Now,
No, I was trying to okay, so for some reason from this other device you're not getting my sound. Okay, fine. This should be okay. Now we start. Okay, so the first question is coming up and you should be able to see the question in your thing and then you have to choose an answer. Okay, yeah, so, okay, that's the idea, okay? I know this is new, so maybe some of you didn't quite get a sense of what's going on. It was too fast, but the question was a requirement and you had to finish the sentence. And I think most of you did not get that. Most of you said may not be required for verification. A requirement is actually required for verification. Okay. And the right answer is The second one, which is a requirement defines what the behaviors of the system may uh, and must be, like what a system is supposed to do. Okay. Are you able to hear me now?
Yes, sir. Yes.
Okay. Right. Let's move on to the next question. Uh, what happened? Screen share is not working.
Actually, we can see only
Okay, so again, I think the timing was a little too short, and the screen didn't show up in time. So the question was, if each of the two modes of a system are stable, then the overall system is not always stable. It can be stable or it can be unstable, right? So the yellow thing here was the correct answer. Let's see if the next. Yeah.
sir, actually, we are not getting that question. Means we can see only those symbols. That is triangle, that square.
Oh, I see, I see, I see. So on the screen share, you are able to see the question.
Yes, sir.
Okay, so last time the screen share did not show up in time at all, right? So
Yes, sir. Yes.
yeah, that was not very helpful. Let's see if in the next question the screen share gives you the question first, okay? Going on to the next question. Now you should be able to see the question, okay?
Yes. Yes.
Okay. Okay, so this was maybe better executed. Exponential discrepancy function is the correct answer is bad because as we saw it blows up too fast. It's too imprecise, right? The approximation is too fast. Some of you thought it's good because it covers all possibilities. That is partially correct because it does cover all possibilities, but it's not good because it's too conservative, right? It covers too much. So there are two sides to it. You want to cover everything, yes, but you also want it to be somewhat precise. You don't want to cover excessive things. Okay. All right. Let's see if there is one more question. I don't think this worked as expected, but Al is leading now with Vivek in position 2. Okay. We have last question, I think. Oh, this is tricky. Say true, false. Cool. Yeah, most people got it. All right, so that was only partly fun because we got the system to work only after the first couple of questions. But hey, this is the first time, so next time we'll be better prepared. Okay. So there's some prize, there's some standings here. Okay, so Vivek is number 1. Great. Okay. All right. Okay. So let's summarize this part of the discussion and maybe take a quick break. How are we doing on time? We've talked for about an hour, maybe a little over.
Yes, sir.
Okay, so summarize this and maybe then take a short break and then we can have another half an hour or so.
Yes, sir. No
Does
problem.
that sounds about right. Okay. So the main takeaway from this part would be that simulation data plus some model information, like what we call discrepancy function, Lipschitz constants, or the Jacobian of the system, can be used together to do formal verification for nonlinear systems. Okay. And this is not does not quite scale to tens of thousands of variables, but it does scales to dozens of variables. So I've been somewhat modest in the claim here. So I say 10 to 12 dimensional systems, but there are some examples of 40, 50 dimensional systems also for which it works. Okay, but also it depends on the size of the initial uncertainty, depends on the sensitivity. As we saw, if the system is very sensitive, then it will require many more simulations and the algorithm might choke. It also depends on the time horizon because each simulation takes time that is proportional to the time horizon up to which we are trying to do the verification. And this is a good area to work on. So there are some early successes, but also there's lots of room for improvement. Okay. In terms of open problems, we talked about reachability and safety, but going from reachable sets to temporal logic properties, where you want to say something happens before some other things, or some event must happen within such and such time. These properties can also be verified once you have the reachable set. I don't think that's a huge leap. With some small algorithmic additions to the reachable set computation, you can handle temporal logic properties. What is more challenging is handling models with inputs. What you have a disturbance input, or if you have a system with the input which is within some bounds, let's say, or which has some continuity properties of its own, how do you handle that? This is a very interesting problem. There are some ideas here, but there are no tools, at least, which can solve that end to end. And then another question that I'm interested in, sort of from the theoretical point of view, is sort of understanding like the sample complexity of this problem. So you saw that every time you want to compute the reach set from an initial set, you have to draw some simulations. And how many simulations you need to draw depends on how close your reachable set is to the unsafe set, and also on the sensitivity and the time horizon. So getting some sort of a theoretical bound on how many simulations are strictly needed to solve this analysis problem would be a very interesting result. Okay. So those are some thoughts on directions for further research. With that, let me pause here and see if there are any questions. And this would also be a good time to take like a couple of minutes break. Yeah. Any questions? Yeah.
Sir, this is Jhalak from KTM University, Bhubaneswar.
Hello. Hello.
Hello, sir. Sir, I want to ask a question. I think that question is related to Boeing 737 MAX. Sir, my question is that with all these things, systems and checks in presence, we have all those systems and checks. How could such a incidence? I mean, what I come to know just by reading some newspapers and Wikipedia article is that there is some problem in its autopilot one of the autopilot modules which was pushing the nose down at the time of takeoff. That leads to the crashes, and eventually it really dusted Boeing's ambition for this particular kind of thing. So, I mean, sir, I am not very, I am pretty new to all this area, but still, sir, I want to know such a big name, such a big company, such resources at its field, how it such a loophole could exist, and that ultimately skipped by all the, even not only by Boeing systems and checks, it is also also bypass the certification processes by across the world, whether it is NTSB or whatever. They also skip that while certify the plane. I want to know that, sir. I mean, how could
Yeah. Yeah, it's a very good question, and it's also a very complicated question because I can tell you several different things. So first of all, let me say something about how certification actually works for aircraft systems. Okay, so for commercial aircraft, there is this document called DO-78C. Okay, so this is a document which basically says it's a standard what kind of testing validation you need to do for any part of the software which is flying the aircraft. Okay, this may not be related to the DVD player that the passengers are using, but anything related to avionics and flight control has to go through that certification process. Now, that certification process is, identifies what level of testing you need to do for the different modules in the software control system. So this system that you just mentioned, ACAS system, I guess, I forget the name of the system, that must have gone through that kind of a certification process. But what is sort of the gap between that process as it is mandated by DO-178C and what we are talking about here is the process does not quite go all the way to showing that the system is safe. Okay. It basically says if your system, if your module or control system has such and such criticality, then you have to run so many tests, and your testing has to be done by, part of it has to be done by Boeing, part of it has to be done by FAA. It is a very procedural process, right? So it says what kind of documentation and testing you need to do. It doesn't quite go all the way to saying you have proven the correctness or the safety of the system. Okay, so the first takeaway is yes, avionics safety has made tremendous progress. In fact, aircraft travel is by far the safest way to travel by most measures. And part of it is because of these regulations that are in place, like this DO-178C that I'm talking about. But even that doesn't quite go all the way to formally proving correctness of the control system in the sense that we are talking about. Actually, there is some plans for making that happen. This DO-178C has some other consortium that is trying to push towards, more rigorous software engineering and verification techniques. But there is also another aspect to it, right? So, certification is a multi-million, sometimes a multi-billion-dollar enterprise. It's very expensive. I've been told that changing even one line of code in a safety critical control system can trigger work that costs millions of dollars, one line of code, because that code has to be then checked by several other engineers. That will trigger some new certification, and that might require some new documentation, that might require pilot training, all kinds of stuff. So certification is a very expensive process. And this I'm not an expert in, but from reading the newspaper articles and some discussions, it sounds like FAA may not have had FAA is the Federal Aviation Agency in the United States, which oversees the certification process for any new aircraft that is getting built. It sounds like FAA may not have had the resources to go through the certification as it is required. You see what I'm saying? So basically, the agency did not have the resources to do the certification even as it is required by the state of the art. And so they may have relied too much on Boeing, and there is this thing called regulatory capture that may have happened where, the company that is being certified is also responsible for part of the certification process. This happens in finance all the time, like big financial firms, banks are regulated, right? But the party that is supposed to do the regulation relies on the bank itself to do the regulation, right? This is called regulatory capture. Once you have that, then it almost becomes like a social problem, right? It's no longer a technical problem, but it's a human problem. Like you're relying on yourself to do the policing, right? And that usually doesn't end well. And this is not based on any fact. I don't know, but there is possibility that these types of things are also happening because the problem is very complicated. But coming back to the technical thing, yes, there is a lot one can do in terms of improving how certification happens for these complex systems, including using formal verification. And there's a lot of successes recently. There's hope that this is going to happen in the near future with autonomous cars, aircraft. Formal verification is being used by AWS, like Amazon's cloud system, in large scale to check security vulnerabilities. It is used quite heavily by NASA. So maybe next generation of aircrafts will come with proofs, not just tests. And that's still not going to be, I don't want to sound as if, formal verification is going to solve all problems. No, it's ultimately human beings are involved, and, these methods can close the gap, but there's a lot of chance that it will improve things. Yeah. I don't know. It's a lengthy answer and doesn't quite maybe say what you wanted to hear, but that's my take on it.
Okay, sir. Thank you.
Any other questions? Or?
Sir, when we design for polynomial systems, then should we convert it into a linear system, or there is another method to go through their polynomial equations?
I didn't get the first part of your question. Can you repeat that? It's something about polynomial systems and converting to linear systems.
Yeah. Actually, till now we have seen the linear equations and trajectory about the linear equations. Now, if we are going for the polynomial equations, like what we are reaching to unsafe state via polynomial equations, then how these polynomial equations will be solved? We have to derive the equivalent linear system for that non-linear system, or we should go directly for that?
Actually, most of the things that I've talked about today are applicable to polynomial systems directly. You do not have to linearize them. So these equations that I was showing you, in fact, are they even have trigonometric functions, right? So these are not linear systems, and you can directly apply these approaches. So, for example, these are not necessarily linear at all. I think the example was in the previous slide. Yeah. But if you can convert the polynomial system to a linear system, it's likely to be much more efficient. Okay. So as I said earlier, the linear solvers scale a lot better. Yeah. So for example, this model, a simple example is it has trigonometric function. And there was another example I think I showed later on that was also polynomial, and that works directly in these approaches. So yeah, I didn't talk about this in detail, but this is also a polynomial system, and you can apply this directly.
Fine, sir. Thank you so much.
Okay, there's a question on. These are great questions, by the way. There's a question on Kalman filters. Yeah, so filtering is very important in state estimation. We haven't quite talked about state estimation, but yeah, Kalman filters and particle filters are used all the time for localization and state estimation in self-driving cars. And the way it connects with verification a little bit is, we talked about this drone example earlier on. Here, for instance, so what's happening here is that the drones are computing some reachable states from their initial states, right? So this circle here, you can think of it as the initial state, and then from there, it is computing the reachable states according to its own nonlinear dynamics. So, but the initial state, how do you get that, right? That comes from a state estimator typically. So based on GPS or a LiDAR, what have you, the drone is computing its estimate of its current state. And that estimate is not going to be exact, right? It's not going to be a single point. It's going to be some sort of a set, or maybe a set with a probability distribution over it, like in the case of Kalman filters. So that's where the initial set comes from. That would come from state estimation. And then once you have that state estimate, then you would apply what we were talking about, this reachability analysis kind of tools to do the prediction forward. Yeah, so this set over here, that's the initial set that can come from state estimation. Okay, any other questions? All right, so shall we move on to the next stage, or what kind of time frame do you have in mind? Another 15, 20 minutes, half an hour?
Yes, sir. You may take 15 or 20 minutes.
Okay, yeah. All right, so what I'll do next is sort of maybe talk a little bit about some of the more general approaches and another application which is interesting. Okay, so far what we have done is we have looked at this verification problem where we know quite a bit about the model, right? We use solutions, and we were also computing this sensitivity, Jacobian, Lipschitz constant, etc., from the model is something you don't want to write down. It's too complicated. It might, in many cases, like even be some code that someone has cooked up. It might be code that people have written over 20 years. And you don't want to go and compute Jacobian for that piece of code, right? That would be a very inappropriate thing to try and do. So what do you do in those cases, right? Right. So let's talk about that a little bit. So here is an example. In the picture on the lower right corner is actually the model of a cruise control system. The details are not important here, but you see there are many block diagrams in Simulink that are connected together to build the cruise control system. And inside those block diagrams, there are more block diagrams, right? So this is like a hierarchical way of building systems, and it gets complicated very quickly. This is a common saying in this world, like all models are wrong, but some are useful. And the useful models can be very complicated. How do you deal with that? Okay, so we came up with a different way of looking at these models, where part of it is treated as a black box, meaning we will not look inside those boxes. Okay, we'll just deal with their outputs. And then there are other parts which are white boxes, meaning we can look at how they're working. Okay, and so to be more specific, think about a control system for a car. Like we can go back to this cruise control system where the logic for when the car is cruising, when the car is overtaking, speeding up, that logic is maybe pretty simple, and it's written in the program that you can read. That's the white box part. Whereas the physics of the car, what happens when it is actually cruising, what happens when it is actually steering left or right, that might be much more complicated, right? The physics there might have lots of things going on. So those would be classified as the black box part. So a graphical way of thinking about it is there is some logic, which is the control graph, which is the white box. And then there is the black box simulator for the different modes. And then if you put these two things together, you still get a hybrid system, but you don't know you don't have like x dot equals to f of x over here. You don't have that. It's a black box. Okay. So how do you deal with this verification problem where you have this combination of a black box, white box system? Well, the idea is we are going to learn the sensitivity of these black boxes. Learn in the statistical learning sense. Okay, we cannot get to Jacobians and all that because we don't have the model, but we can still run the black box. We're going to collect some data from the black box, and we are going to learn a sensitivity of the black box with some probabilistic guarantees. The guarantees are not going to be as good or as tight, as deterministic as the guarantees we got with the Jacobians, but nevertheless, there's going to be some guarantee with some probability, and in this case, maybe that's the best we can do. Okay. So how do we do this in a nutshell? We pick a shape of the sensitivity function. So here we have chosen this exponential shape, e to the at plus b. And then if you remember, this is the definition of our beta function that we've been talking about, right? So this is the beta we had in the first part of the lecture, but now we have also added a particular structure to this beta, which is this exponential structure. And then if we take log, divide and then take log, then this looks like a linear equation. It's the equation of a straight line. Everything over here these are constants. This is particular data point that we can get from particular simulation runs. X1 of t is a data point, x2 of t is a data point, x10 is the initial point, x20 is the initial point. So everything on the left-hand side is a constant. So you get a number, you take a log of that, and then we are trying to figure out what A and B are going to be from a bunch of these numbers. Okay. So if you look at it, it looks like a straight line, right? Some y less than equals to ax plus b. So basically, we want to find the a and the b to fit this data. This is actually a very well-known problem in machine learning, in this literature on probably approximately correct learning or pack learning. This is called learning a linear separator. We want to find a straight line which is above all these data points. Okay. So we are going to learn a linear separator, and we just use the pack learning theory from which we then get that given any training set, we can learn a beta function of that particular shape by solving a linear program. The precise guarantee will be like this. So for any epsilon delta, this is the typical kind of guarantee you get from pack learning. For any epsilon delta positive, you can find a large enough number of samples in such that with probability 1 minus delta, the algorithm will find a linear separator, meaning those two parameters A and B, such that the probability that these are bad parameters, meaning the straight line does not give you an upper bound on all these points, is very small. Okay, so that's a long statement, but basically it says that the probability that you have learned a sensitivity function which does not work is very small. Okay. You can plug in these numbers, epsilon and delta, for example, for epsilon 0.1% and delta 1%, the number of samples or trajectories that you will need is about 5,000. And in practice, we found that even with like 20 trajectories, you can get like up to 99% accuracy for this beta function. Yeah, so this sort of fills in a gap from in the previous story. The big algorithm is still going to work the same way. We are going to partition the initial set, draw in individual trajectories, and then do this bloating based on the sensitivity function as we did in the first part of the talk. But now the sensitivity is coming from this learning algorithm. Okay, so now let me just, again, we're running out of time here, and I'll just talk about another example to wrap things up. Actually, there are a couple of examples in my slides. I'm going to skip over the first one. This was about a very practical anti-lock braking system that we wanted to study. But let me tell you about another one that is a little bit more interesting. It's actually very recent. We just finished this work. This is about a auto ground collision avoidance system that is used in some of the more advanced aircraft. All right, let's see. Some of these animations are crashing on the iPad. That's not a good thing. Okay, so the system, let me tell you about the system first, and then I'll show some of the results. So this is called the Auto GCAS system. GCAS stands for Ground Collision Avoidance System. This is a built-in autonomous system inside fighter planes, like the F-16. And what it does is, if the aircraft is getting too close to the ground, then it lifts up the nose of the aircraft and stabilizes it at a particular height. It's an extremely important system in fighter planes because what can happen is, let's see if this video plays. Nope, some of the videos are not working. Anyway, it doesn't matter. Basically, this video is a live recording of a fighter aircraft's cockpit where you see it sort of nose diving very fast, and then the GCAS system kicks in and it stabilizes the aircraft at a good height. So what can happen is when these fighter planes are doing very high G maneuvers, right? When it's turning very fast or going up very fast, then the G forces experienced by the pilot can be very high. It can be 5 or 6 times the normal G, and all the blood from their brain sort of drains and they can pass out. They can become unconscious for a short duration of time. And during that period, the plane can do all kinds of very dangerous things, including, go all the way crashing towards the ground. And that's where the GCAS system is supposed to kick in and basically save the pilot and the plane. So apparently there's been lots of studies using this. There are more than 10 confirmed saves using this Auto GCAS system. And now we have a project with the United States Air Force where we are trying to verify that Auto GCAS system using our technique, in fact, the techniques that I just talked about. And they're interested in it because they're going to combine this GCAS system with other types of autonomous systems on the aircraft, and they want to make sure that they don't interfere with each other in a negative way. Yeah, so just to give you a sense of how complex this system is, this is certainly a black box system. We don't have access to the actual aircraft's dynamics in the form of a differential equation. It's all described using block diagrams and certain components that we cannot really look at because of obvious privacy and security issues. But we still want to be able to check certain properties of the trajectories of the aircraft. So the model we are working with has 16 dimensions. You can see them here. Yeah, and so what you see in this figure, I think the PowerPoint is slightly lagging behind what you're seeing here. Yeah, so what you're seeing here are 3 plots. The outer orange plot is showing the actual reach tubes that are computed by the algorithm. Inside, you see the actual trajectories. Here we are plotting the airspeed. Among the 16 variables, one of the important ones is the airspeed, the speed at which the aircraft is moving. And the traces are shown inside. There are 2 different shapes of this discrepancy function that we are using. Those are sort of shown in these 3 different plots. Yeah, so yeah, these are the other variables like angle of attack and angle of slide slip. The big point is the system sort of captures the reachable set in a very precise way, even for this high dimensional system. Yeah, I think you don't have to look at all these plots. They're more or less the same story here. Okay, so let me skip over synthesis in the interest of time, rather spend more time sort of discussing open questions and things like that. If there is some interest in synthesis, I can come back and talk about this. Okay. Right, so this last part is a natural addendum to what we were talking about before, where we don't have models of the whole system. We can learn the sensitivity of the system from data, and we can get probabilistic guarantees on the sensitivity. Particularly, we use pack learning, but other people are also looking at deep learning methods for finding sensitivities of the system. And then once we have that, we can combine it with the regular verification algorithm. Once again, important open problems here would be how to handle systems with inputs, open systems. And again, theoretical understanding of sample complexity is going to be quite important and interesting. We are looking at real-time control synthesis using these approaches. I know we didn't get to talk about control synthesis today, but if you're interested, I'll be more than happy to point you to the papers or give you some ideas about how verification fits with synthesis. And another interesting direction is this trade-off between system identification and verification. So normally, the way this is done is you first develop the models of the system. So that step is called system identification. And then you do verification or synthesis. But of course, the quality of the models that you develop has a tremendous amount of bearing on the verification algorithms. So a more natural way of doing business would be to look at system ID and verification within the same framework, right? How much do I need to invest energy in creating models in order to benefit my verification, right? This is an interesting trade-off question that can be studied studied carefully. Okay, I think I'll stop there. Again, it has been a great pleasure talking to you all, and it's a Sunday morning, right? So thanks for joining and making time to listen to me speak about these topics that I'm very passionate about. And I'll be very happy to answer questions or have a follow-up discussion, continue discussion over email, and in any way that I can help, I definitely am available to help you achieve your goals in research or education on these types of topics. Yeah, go ahead.
Yes, sir.
Go ahead. Go ahead.
So participants, if you have any question, you can ask. Sir.
Yeah, there was, I think, a question about a book, and this is a very timely question. I'm happy to say that I'm actually writing a book. It's a little bit of self-promotion here. This book is actually also tagged over here. It's called Verifying Cyber Physical Systems, A Path to Safe Autonomy. And you can find this on Amazon. I mean, the book is not yet published. It's going to be published by MIT Press in February, but it's already on Amazon, so you can, bookmark it or something like that. But there are also other books. Okay, so Professor Rajiv Allur has a book on cyber physical systems, which covers modeling in different kinds of modeling. There is a little bit of focus on verification also. I think my book covers more of verification. But his book also, I think, gives general introduction to real-time systems and things like that, which are not in my book.
Okay, so I think there is no question. So I want to thank you, sir, from the bottom of my heart for such a nice and elaborated lecture. And I hope the lecture will help the participants to choose formal verification as a research career. I also thank you for your effort for this lecture and having a quiz. Uh, so
Great. Yeah, the quiz didn't quite work as smoothly as I wanted, but now I know how to do it. So next time it will be better. Yeah. Thanks for participating in it, nevertheless.
So I want to thank you for giving your time and for this nice lecture. Thank you, sir.
Great. Take care. Thank you very much for having me. Yeah. Bye-bye.
Thank you, sir. Bye bye.
Okay, dear participants, feedback form will be available in your Google chat. I think within 5 minutes. So just wait for 5 minutes and fill. And I think next session will be just a second. So next session will be at 4:30. So you can join us approximately 4:20. Okay, and. So kindly fill the feedback form. Thank you. Wait for 5 minutes. Feedback link will be available. Wait for 5 minutes.
Literally, I'm just giving you that. आते हैं ना फीडबैक के लिए तो फीडबैक के नीचे कोई नहीं आया ना क्या हो उसको नहीं देखा मुझे मेल आते रहते हैं ना मेरे बारे में ज्वाइन कर रहा हूँ मेरे बारे में वो मैसेज आता है ठीक है आप ही कह रहे हैं हम उनसे एक के बीच में कोई आया होगा नहीं नहीं फीडबैक फीडबैक करते हैं हम जो फीडबैक फीडबैक चूतिया हो गए हो एक बार दे के रिप्लाई छोड़ दो वो करने दो चलो मैं रात में जल्दी आना पड़ेगा कल लैब है ना लैब के लिए कुछ करना पड़ेगा क्या करना है नहीं क्वेश्चन मतलब ये लोग यहाँ पे इन लोग क्या बीमार वालों से बैठना पड़ता है मेंटली तो नहीं रहे हैं नहीं मानना कैसे से साथ में करोड़ नाम लिखना है एक्सेप्ट कर लो आदमी चाहिए ये 63 गई नहीं क्या नाम 63 अच्छा वो मैसेज यहाँ तो सब ये बोलते हैं हाँ मैं वही बना रहा हूँ नहीं सर, वो भैया बेटा का जगह बुढ़े हो गया। आपके पास आ गया, मैं एडिट कर दूँ। मुझे एक्चुअली इस साल का नासिक करना है, एंजॉय कर लेता हूँ। अच्छा कुछ रिसर्च ही करते हैं। इस साल हो गया। मैंने हम सोचा कि इसमें हाँ बिल्कुल लिखो, लेकिन मैं अपडेट कैसे काम करूँगा? इसमें सीरियल कितने जर्नल लिखे हैं ऊपर? 28 जर्नल लिखे हैं। 72 अच्छा इसको ही देखिए यहाँ लिखा हुआ, देखो मैं निकाल देता हूँ। ये इसकी कोई वो है पेज, यहाँ इसमें ये है ना रमेश? हाँ करते यार। अगर लिखना चाहो तो इसकी बीटेक लिख सकते हो, इसने वहां से करिए इसी नंबर से। ये डाउट है कि फिर मैं एमटेक नहीं बता पाऊंगा इससे। ऐसी लैंग्वेज बीटेक कराता है। आपका बीटेक है? नहीं बता रहा ना भाई, मेरा ना बता रहा। 78 से 81। 81 बीटेक की वही से क्या होगा? उससे पहले इसने पीएचडी करी है भाई ने, बीएससी करी है अप्लाइड साइंस में 75 से 78 में। चलिए वो एमटेक की वही से क्या होगा, इसलिए सर को जानते हो। कौन सा? नहीं, बीटेक के बाद सीधा एमटेक किया भाई मेरा, पीएचडी आईआईटी बॉम्बे से। कहाँ से पीएचडी किया सर? वैसे वैसे शायद। अबे देखो सही से, यहाँ देखो लिखा सिर्फ आईआईटी यार। नहीं वहाँ पे देखो उस पेज में क्या लिखा है? उस पेज में थोड़ा घपला है, यहाँ ये लिखा है पीएचडी इन कंप्यूटर साइंस एंड इंजीनियरिंग, उसके बाद लिखा आईआईटी बॉम्बे। हाँ सही है। बीटेक इन इलेक्ट्रॉनिक्स एंड इंजीनियरिंग आईसी बॉम्बे, मुझे लगा वो आईआईटी बॉम्बे ऊपर वाली लाइन पे नहीं लिखा है। फेलो है ना, आई फेलो वो लिख देते हैं। कहाँ लिखा है? Real-time systems and Journal of Embedded Systems, keynote talk in many international conferences. अरे कल कौन ले रहा शाम को? उठा भी नहीं होगा। सुनना रहो बेटा मेरा। Sorry. Sorry. किसको पढ़वाते हैं? या श्रीगुरु श्रीगुरु से जैसे हो जाएगा तो सिर्फ एक ही बचेगा तुम्हारे साथ। अच्छा अच्छा अपना मुझे फंसा के मौज ले रहा है मुझे पता ही नहीं मुझे पता है फंसे हुए हैं वो जानते होंगे अभी अभी उनके ऊपर क्या बीत रहा होगा नहीं वो मतलब चैलेंज कर सकते पॉजिटिव लगे ऐसा नहीं मतलब कि फंसा देगा हमारे वाले को बिल्कुल हाथ में रखेंगे ना मैं आपको बोला मेरे को कह रहे यार तू मेरी कच्ची करेगा क्या करेगा कच्ची करेगा लोगों को लगेगी वो सारे खड़े हैं उनको लगेगा ऐसा नहीं सर हो सकता है क्या फिर देखते आज मुझे डर लग रहा था कि थोड़ा वो चार्ज बढ़ रहा है और यहाँ पे तो मुझे थोड़ा मुझे एक दिन अलग क्वेश्चन पूछ रहा हूँ कोई जवाब नहीं दे रहा मुझे लगता है कि आज हमारे फर्स्ट मैंने बोलेगा कि ज़्यादा कर रहा है हमारा नहीं ताकि करना तो आपको आता नहीं है उसको आपको फिर कल सुबह वाला खाने अरे कहाँ गया क्या नहीं कैसे दे दूँ तुम्हें पता चल ही जाएगी मुझे नहीं पता आपको फिर भी नहीं वो तो वो नीचे को साइड से ही बाहर में है ना कैसे ये तो हम नारायण बच्चों की तो बच्चों का है उनके इंटरेस्ट है नहीं वो जो आदित्य करते हैं लड़की है उसको देख रहे ये लोग सारे क्वेश्चन को क्वेश्चन करके बोलेंगे क्या मतलब ये देखो ये तो मजबूरी है मतलब अप्रिशिएट करना चाहिए क्वेश्चन का तो फ्यूचर क्वेश्चन गलत था वो टेम्पोरल की तरह भाई को स्लाइड उधर पड़ गई जब किसी को स्लाइड उधर पड़ जाए तो समझ के तो फ्यूचर क्वेश्चन है पूरा जो क्वेश्चन है मतलब क्या है कि वो उसके लिए तैयारी मतलब वो उसके आसपास भी नहीं अगर आसपास भी होता तो बंदा हवा में बोल देता है स्लाइड नहीं बोलता उसके लिए जैसे मान लो मैं सेट पढ़ा रहा हूँ ठीक है और मैं सेट में जाके वो जो है ना a + b + a + b - x में पहुंच गया मुझे कुछ पूछना है कि सब्जेक्ट क्या है, फिर मैं पीछे गया और ये तो फिर भी मतलब कहीं ना कहीं रिलेट किया था, ऐसा समझो आप जैसे सी में पढ़ा गया प्रोग्रामिंग छोड़ के पाइथन प्रोग्राम पे चला गया, नहीं नहीं उस टाइम का नहीं, फिर नहीं आप एक चीज समझो, अगर आपको कोई क्वेश्चन नेगेटिव पूछना है आप आंसर एट द मोमेंट दे देते हो, फिर कहते हो ओके आई विल टाइम फॉर मोर क्वेश्चंस, अगर मुझसे कोई सडनली पूछे सर सिस्टम का डाउट हो फिर क्या होता है, प्रिंट लेवल पे आपको सिस्टम का डाउट हो फिर ये एक आउटपुट का तरीका है, और जाने फिर मैं सेलेक्ट होता हूँ ये एक्चुअली में ये पैरामीटर पास हो रही है, तो वहाँ जाकर समझाता हूँ बाहर तो स्लाइड बोलता हूँ आउटपुट का नहीं काम पे जाना तो गलत, पता चला कि नहीं मार्क्स से निकल रहा है गलत है, नहीं ट्राई टू दिलाओ मार्क्स छोड़ के करने क्या नहीं हो गया 17 कॉन्फ्रेंस दिखा रहा है 12 जर्नल 17 कॉन्फ्रेंस 12 जर्नल I1 I2 क्या है ये मतलब जो आपका कौन है अरुणदेव? कौन है अरुणदेव?
Good morning, sir.
Hi, can you hear me?
Yes, sir. Good morning, sir.
Uh, Good evening. It's evening time for you, right?
Yes, sir.
Can you hear me well? Is it okay, or I should use the microphone?
Yes, sir. It is okay. It is okay. It is fine.
Okay, so I will not use my camera because one is I'm running from my office laptop where the camera is switched off.
Okay, sir. Okay.
So you're working from your office. What I see background is your office or home?
Sir, it is office.
Office. Okay.
So good evening, all. It is a great pleasure for me to introduce the speaker of this session, Professor S. Ramesh. Professor S. Ramesh is a technical fellow in General Motors R&D division. He received his PhD in computer science and engineering from IIT Bombay. He has more than 30 years of teaching and research experience in various reputed institutions like General Motors, IIT Bangalore, University of New South Wales, and IIT Bombay. His research interest includes embedded software modeling, testing and verification, distributed systems, and software engineering. He has published more than 100 publications in the areas of modeling, verification, and testing of embedded systems, distributed systems, and hardware circuits, and more than 10 patents in automotive embedded software modeling, analysis, and testing. So now I request Professor S. Ramesh to kindly join us for a great session. Thank you, and over to you, sir.
Thank you for this nice introduction, Dr. Behera. It's a pleasure to be with you all. So hope I think you're working even on Sunday, right? Right. I see that people are joining still. Should we give a couple of minutes, or
Yes, sir.
we can just go ahead?
Yes, sir. Yes, sir.
Oh, okay. So let me wait for a few minutes. So this is what? This is the third or fourth day of this course?
Sir, it is the third day.
Third day. Okay. So you have one more day,
2 more days, sir.
2 more days. Okay. So how many participants totally? I think I see 31 at least now. Yeah.
So actually, we are also broadcasting it on YouTube.
Oh,
So some of them may have joined there also.
I see. Okay. Okay. Let me share my screen and let me know where do I present now. Okay, so I should say present now.
Yes, sir.
Mm, Can you see my screen?
So actually, it has not come up right now.
Is it showing signs of coming up?
No, sir. No.
Oh. So when I I see. I have to say share. Okay.
Yes, sir. Now it is coming.
Try now.
Yes, sir. Yes.
Okay, good. So welcome to all, and good evening, and good afternoon, and good morning, wherever you are joining from. So in this lecture, I will highlight some of the important things with respect to modeling and analysis and verification of cyber physical systems. I know that this is third or fourth day of your this series of lectures, so there could be some repetitions. So just bear with me. Can you see my next slide, Dr. Vera?
Yes, sir. Yes.
Okay, perfect. So I think it's working. So let us dive into this. So CPS, cyber physical systems. I think that's what the focus of this mini series is. So I will give some kind of perspectives, which could be overlapping with some of the perspectives that you have seen over these 2 or 3 days with other lecturers. So feel free to ask me any questions. You can probably fill in some chat windows, and Dr. Behra, please feel free to stop me at any point. And if there are some things that is not clear, or as I move around my computer, there could be some noises or hearing issues. Feel free to just interrupt me.
Yes, sir. Definitely.
Right. Okay, so CPS features are what are known as reactive control systems. Essentially, underlying in their computation, there is a cyclic computation, right? Unlike traditional systems, traditional software, they're expected to start at some point of time, receive some inputs, do some computations, and then produce some outputs, and then terminate there. Termination is a bad behavior for CPS, right? They are not supposed to terminate. They need to have an ongoing interaction with the rest of the world or the rest of the environment, which could be physical, right? Keep on doing something. So that's why cyclic computation is underlying there. And typically you have the sense, compute, actuate cycle, right? This is the traditional CPS feature, right? I think this lecture material, this was prepared quite a while ago, now over the last several years. So I'm trying to update as things evolve. So I think the traditional CPS, you have sense, compute, actuate. Now, what is going to happen in future is that the sense is going to be generalized into perceive, right? Perception, planning, and action or control, right? So essentially, as we are moving into the AI-enabled world, your CPS is going to have an important element called AI-based perception system. So you need to perceive the situation, which of course involves sensing, right? Now, when we generalize that sense into perceive, so you are going to the CPS is expected to do many more things. Many of the CPS, for example, if we take automotive, which I have been working on, automotive, a vehicle on the road not only senses, it has to perceive that whether there might be an accident in the next few minutes, right? That perception is a challenging one, especially when you have complex road environments. So it might be perceive, plan, and execute, something like that, this paradigm. So often many controllers are sensing and actuating different things that affect the external environment, right? So that the plant, as we call it, so the plant is an important element, right? Cyber physical systems. The plant is the one which is being controlled, which is being sensed, right? That the plant doesn't mean that it's a kind of single plant. It could be distributed. You can imagine a plant to be the entire environment on a road, for example. Now, if you are talking your cyber physical system to be the automotive control systems, that the vehicle software is your control system, but the plant is the entire world surrounding that vehicle, right? It of course includes the vehicle, the physical vehicle. It could also include the environment, right? The people around, the other vehicles around, the buildings, the sunlight, the signal conditions, and so on, right? So it's often distributed, right? And as I said, that its determination is a bad behavior. Another important feature of CPS is that it is concurrent and distributed. Now, I already talked about system and environment running concurrently, right? I think this is another important distinguishing feature from the traditional way in which software is being built, right? Software, you assume that some inputs are coming. That is the only point at which you care about the environment. After that, you compute something and then just produce the output. Whereas in the case of CPS, not only the system, which is controlling, which is sensing and controlling, might be running concurrently for different reasons. One could be, now you want to parallelize computation so that they can faster response you may need, or it could be doing multifunctional things, right? So multiple features might be there. Now, if we take again, giving an automotive examples, an automotive embedded system or CPS is supposed to be doing multiple things, right? It is sensing the road and then trying to do some actions, and it could be also seeing that what the people inside the vehicle are doing, or the driver is asking for, right, and so on. So it has multifunctional. A natural view of developing systems is to do them as concurrent systems. And the environment is distributed in space, right? It could be that so you might have power plants distributed across the entire country, and you might have a centralized computing systems computing power, responding to the kind of power needs at the grid and so on. And then you might be trying to control the way in which how much power to be produced, how much resources to be utilized at different points of different centers and so on. So you can imagine them, right? It could be a centralized controller, a small space in your lab, or it could be in the kind of entire system connected with internets and other communicating devices. In the case of automotive, I can give another example is that vehicles can communicate with each other. Now you can think of a CPS to be the control systems which is controlling the individual vehicle, but that individual vehicle might be communicating with other vehicles. So it might be talking about in a road, maybe that 1,000 meters down the line, that there might be some accidents. This vehicle might be responding to that. It might be changing its direction. It might be taking another navigation route and so on. So you can imagine them to be highly distributed. Right. So now the third important feature is that hybrid system. Right. So I think this word you might have heard of in this series. So it's there are this hybridness. Hybrid nature is coming from combination of digital and discrete and continuous thing. Right. Environment is typically a physical system involving evolving continuously, while control is typically implemented in a digital platform. So the control is necessarily discrete for various reasons. Right. In the early days, 50 years before, the control was also analog, right? But today, digital has its own advantages. So it has become digital control. Whereas the environment that you're controlling, if you take a thermostat, the temperature is one of the parameters that you're controlling. Temperature is a continuous entity, right? So environment is a physical system evolving continuously. So this also poses some challenges, right? A discrete system cannot continuously interact and then find out the instantaneous state of the environment. So when you are designing control systems, you need to take into account this. You are doing a kind of sampling of the environment, right? And timely response to external situations, right? So I think this also is a real-time system. So I think I will be talking about that. Imagine a delay of few minutes in a pacemaker. Now you can talk about a pacemaker which is controlling the heartbeats, and if there are any delays in controlling that, there could be catastrophes for the individuals. The similar kind of timely response necessities or demands you could imagine in an automotive or aerospace context. Right, they are connected all the time. Right, connectivity is an important requirement. Connected means connected to the rest of the environment is responsible for. Right, connectivity is an important requirement. Open interfaces with multiple standardized protocols. And since the openness is there, security vulnerability is also a serious concern. And this is becoming much more serious now, much more in the kind of connected world. Now imagine if your pacemaker as a kind of standard device and somebody can go and control, there could be catastrophes. Similar things happen in the kind of automotive systems. Right, earlier automotive systems were very localized, individual control systems, and it was not talking to anyone else outside. But with the kind of open interfaces, there are possibilities of controlling your vehicle externally, and that could also lead to accidents and so on. Required to be fault tolerant. Right, this is another important feature. Controlling physical systems that are evolving independent of the controller. Right, failures at every level, software, hardware, interfaces need to be taken into account. Right, so that's why these systems are designing these systems become much more complex. In a kind of traditional, localized, small piece of software that you are developing, you can assume a lot of constraints on the inputs because very specialized users, specialized inputs are being given, and whereas these systems are expected to work in all situations. Right. I think another thing is that CPS features, again, they are intelligent systems. Now, as I said that, I was hinting at AI algorithms and AI-enabled systems. Right. When you are going to do perception of your environment, you may be sensing something, and then accordingly, you're going to perceive that, maybe something is going to happen, and instruct the control systems to accordingly do some corrective actions. Right. And they could be also, even humans could be in the loop. Right. Sometimes people say that human in the loop is causing problems. Many of the unsafe situations that are happening in complex embedded systems is that there are human errors, right? I think pilot errors, you might have heard of. Now, often, complex computations are being done now by the control systems. There is a bit of intelligence that is built in, but since you are not 100% sure, you always keep the human in the loop, right? Now, people are talking about in the automotive context driverless vehicles, but no, you're not going to see the driverless vehicle soon. Not till for some time to come, the drivers are going to be in the loop wherever the system is not able to do anything. The driver is going to be handed over control, right? So the human is going to be in the loop, and now there are sometimes situations arise, unsafe situations, and accidents could occur because the driver is in the loop. And of course, the other aspect is the AI algorithms. AI algorithms have their own imperfections. And the third one is that when the human is there and when AI algorithms are there, they are probabilistic and often unreliable. Now, for example, there's a kind of heavy, if you take supervisory AI engines, then their behavior depends upon the training data, right? As you might have heard of. And now there could be conflicting requirements, right? Often this is what happens. There is a whole area in the case of AI-enabled systems, what is known as safety of the intended function, right? So the intended function, so you might be correct with respect to your requirements, but the requirements themselves might have some unforeseen situations, right? So because of partly because of this open nature, right? Now the entire world is open. You cannot conceive of all the things. If you take human beings, even human beings are subjected to in a kind of open world. There are situations where you do not know whether you did the right decision or not. Now going forward, in retrospect, you might be thinking that you could have taken a different decision. It's the same kind of issues that are going to happen with AI-enabled systems, right? Because we do not know what is the effect of a particular situation or particular decision that you have taken, right? These are some of the conflicting things and complex situations that demand modeling and implementing these control systems. Right, and other concerns for CPS, correct functioning is crucial, right? These are safety critical applications. Now imagine pacemaker to start with, and individual life is involved there. If you take automotive systems, a vehicle control malfunctioning of the vehicle control systems, right? Now could cause accidents, and it could cause not only the driver in the vehicle or the passengers in that particular vehicle, it could also affect others. And aerospace and nuclear power plants. Now, if there is a blast in the nuclear power plant, that could affect the entire neighborhood. So, special set of additional requirements like safe behavior under failure conditions. Right? Some of you might have heard of fault failure mode effect analysis or fault mode effect analysis, FMEA. Right, this is another entire branch of branch of engineering which you need to do, right? So you need to see that what are all the faulty modes that are there in the system, and then what are their effects, and then you have to take into account, and build some kind of detection mechanisms, diagnostic ones, whether the situation is going to lead to any failures, and then if there is going to be a detection there has to be detection of the failure, and then appropriate corrective action has to be taken. Right? Now you cannot go on at the last moment, hand over control to the human being who may not be equipped to deal with all the situations. Right? Diagnosis, prognostics also. Right? Maybe that situation may not happen in the next minute. It may happen a couple of days later. So you need to have some kind of prognostic algorithms. Now, of course, I talked about security vulnerables. Right? So the additional requirements, these requirements are also called as para-functional requirements, right? Timing, not only the functionality is important, but also other non-functional, as they call it. They are also there. Those requirements also become bigger and bigger. Sometimes they are much higher than the functional requirements, right? In the industry, for example, that people spend a lot of time. Now there's a whole set of engineering organizations, sub-organizations, which are spending time on this safety, how safe it is. Now, when you are going to transfer control from human beings, right? Most of the CPUs are going to be like that, right? You're going to transfer control partially and in future, maybe in its entirety to the machines, right? To the electronic and software and hardware, right? The software and hardware are subjected to different kinds of failures, right? When the human beings are also subjected to failures, human beings are also uncertain. But one big advantage with human being in the loop is that you can always blame the human, right? You can always go and uh, you know tell that it is a human error, that the human has to be punished. You fine him depending upon the criticality, or you jail him and so on, right? Whereas here, what you are going to do, right? When a CPS system which is controlling the vehicle, whom you are going to blame, and when a human fails, it could be only one system, right? So imagine a human driver makes a mistake, only that vehicle is faulty, but the CPS control system fails. Imagine that the CPS control system controlling the vehicle, it is there in millions of vehicles. All those millions of vehicles are at fault, right? Whom are you going to put the blame on, right? And see, these are some of the issues, some of the complexities that come into this. When you are transferring control from human to machines, you want to make sure that random hardware failures do not affect the functionality, or systematic failures in design do not affect the functionality and so on. Right. Other concerns of CPS, stringent resource constraints. Typically, you would like the control systems to be very compact, simple processes, limited memory, quick response, good throughput, low power, and easy time to market. Depending upon the applications. Unless you bring some control systems to market, you may lose the market. Your competitors might come and occupy that space. So these are some of the design considerations. So when we look at the CPS system, so the system development is essentially involves the process of arriving at a final product, conforming to or satisfying all those stringent requirements that we talked about, right? Final product from requirements. When you talk about requirements, I think this is one of the things people have started realizing is that requirement is the weakest link in all the aspects. Typically, even in your right, if you are a student, your requirements for a software are given by the faculty. Often these requirements are handed over to you by saying that write a program or write a software, or for a project, some ideas are given, but not everything is spelled out. As you start building these systems, you get a lot of doubts. So you need to engage the stakeholders and ask about various things. And if there are any mistakes in the requirements, another reason for requirements being the weak link is that any mistake in the requirements is going to affect your entire design development. You spend a lot of time, hours, resources, and you build a system. At the end, if you are going to do the validation or verification, and if you find some bugs, it could be related to requirements, right? Then what you have to do, you may have to go back and completely redesign the entire system. So it is better that the requirements need to be very precise, right? But in reality, they are vague ideas, algorithms, off-the-shelf components, or it could be that now you already have a system, you are going to add some functionality to that, right? You might not have appreciated that existing system. The existing system have been developed 5 years before. Again, now it might have suffered 5 years before the processes that were used for developing the product might be quite different from today, right? Because the entire thing is evolving. New things, new tools, new methodologies are being practiced. So you might have a poor understanding of that existing system. When you're going to add functionality, the functionality could be there could be some issues with the resulting system. The issues could be arising out of your poor understanding of the previous system, or it could be a poor functioning of your own system, right? Whom are you going to blame? Right. Now, in contrast to the requirements, if you look at the final product, right, system components, they are very precise. right? Because the system components are expected to be deterministic systems. Of course, now if you are going to bring in the AI things, there could be some uncertainties and non-determinisms that might come in. But in general, they're reasonably precise. If you give a sequence of inputs, they're expected to produce some sequence of outputs, unlike your requirements, which are informal. Right? This is another challenge, that you have. System components, when we are talking about, just to set the scene, CPS components could be hardware, control algorithms, software platforms, AI algorithms, encryption methods, and so on. Right? Hardware, they are programmable processors, controllers, and DSP, standard and custom hardware. Now, if you take AI algorithms, you could have even GPUs, right? Control algorithms, PIDs, PI controllers. Now, that's how you started in the early days. But now we are talking about model predictive control or your reinforcement based algorithms. Now, controlling things. Software platform, real time operating systems, middleware, safety architecture. Right? The system development is essentially involves multiple steps, requirements gathering and documentation, functional decomposition, architecture selection, right? Choice of the processor, standard hardware, control algorithm selection, mapping of functionality to hardware and software, right? So you're required to start from very high level requirements, because when you are going to, which functionality you are going to distribute to software and which to hardware might depend upon the performance of the whole system. So you need to do mapping, right? People talk about hardware, software, co-design, right? Now, 5 or 10 years before, this was a hot area. And this is in the kind of embedded context. Development of custom hardware and software, communication protocol between hardware and software, and prototyping, verification, and validation, right? These are different steps that are involved in the system building. And these are the design choices that you need to make. Choices in components, processors, DSP chips, FPGAs, standard components, many different choices in mapping, right? You could have fully hardware solutions. Hardware solutions, more speed, cost, time to market, but less robust. Or standard hardware development, right? This is standard hardware development. It could be fully software solution, but slow, less time to market, cost more flexible. Standard microcontroller based development is also possible, right? You take the standard microcontroller and then you write your software and then fire it onto that controller. Our desired solution is often mixed, right? Optimal performance, cost, and TTM. Design is more involved, takes more time. As I said, co-design of hardware, software, and control. System partitioning is also a difficult step. Now, the people need to do what is known as design exploration. Right? When you're doing design explorations, now you have to think of alternative designs. So whether function 1 can be in hardware or software, compared to that function 2 could be in software. So then what is the resulting performance metrics? Are they up to the mark, whether it meets the requirements and so on? So then you have to go and try alternative designs. So you need to have evaluation criteria and so on. So these need to be set in right in the beginning. Anyway, design practices supporting exploration and evaluation is essential. Right? Of course, correctness analysis is also all the time crucial. Right? Now, this kind of alternative designs and so on, now when it comes to that, I think that is where this modeling paradigm becomes very important. If you are going to have the only means of measuring performance is having the end system, right? The end system, if it is a mixture of hardware and software, if it is software, it is relatively easy in the sense that you can go back and rewrite software. Even then, that is going to be costly. But imagine that you have already manufactured a lot of hardware solutions, right? So the entire thing becomes waste, right? So that is why I think that's the kind of motivation that I'm trying to bring in here. What is the motivation for having an intermediate level, which is as easy as software, but it's not as complex as software? That is what is called models. Right? right? And CPS development, if you look at, it involves both hardware and software. Both have taken different routes, fundamentally different. If you take hardware, hardware is finite state, hardware is tangible. Software is infinite state, in potentially infinite state, it is abstract. And the development processes were quite different, quite a few, before the software hardware co-design era, 10 years before or something. But now it is converging. So what they are converged into what is called as model-based development. Right? I think software development, so I think in the 1970s and so on, there is something called software crisis was there. Large number of complex applications, little experience, huge gap between requirements and final implementations, lack of methodologies, little way of planning, time, schedule, cost, quality, right? I think that is where this idea of having high-level programming languages, which gave way to modeling, came in. Right? I think if you take software engineering, there's a large body of academic and industrial research and experience over more than 20 years. Emergence of software engineering as a discipline. Various concepts came in. When I was studying, structured programming was one of the important concepts. Information hiding, object-oriented programming, various methodologies, different models of development like waterfall model, spiral model, V-cycle. Now, one of the new models that are being picking up in the industry, especially automotive industry, is that agile, right? Going agile, you might have heard of that. There is another model of development. And model-based development methodologies is one of the outcomes, right? So I would not say recent, it has been there for the last 10 years. You might have heard of words, maybe in this lecture or earlier, like, or especially in the context of embedded systems, RTUML, ROM, or structured methodologies, RT, SAD, and so on. Many of them are real-time model-based development methodologies. UML is probably one of the important ones, and recent development of UML is what is called as SysML, right? SysML is for the entire system. Now people are talking about model-based development not only for hardware, software, but rest of the physical system also. Right? I talked about CPS, assuming that physical system is constant. Right? Now, but if you take an automotive company like GM or any other company, they are also building to some extent part of the physical system, namely the vehicle, right? The design of the vehicle. So there are a lot of other engineers from other disciplines, not only software and hardware engineers, but also it is full of engineers from, say, for example, chemical engineering. Now who are building, earlier they were doing combustion engine, a lot of electrical engineering. For electric vehicles, these people design electric motors, right? And there are, so you need to design doors, you need to design your front bumpers and so on. So these are also being designed. So people are today talking about building all these systems from scratch using a unified methodology called employing tools like SysML. Entire system. When we talk about the system, it is not only hardware and software, but also the plant themselves. Even in order to have a hardware and software-based controlling a physical plant, don't assume that the plant is already existing. So you have the flexibility of even going and redesigning that plant. So when you're talking about hardware, software, code design, so we need to talk about, right? In fact, SysML and Industry 4.0 efforts are essentially towards core design of the entire system, right? Entire CPS, which involves starting from high-level requirements for example, in the case of automotive, the entire vehicle, which includes not only your hardware, software controllers, but also the electric motors which are driving the vehicle, the doors, the panels, the glasses, everything included. Right? And if you see that, it's not only look at the variety of the end system. The end system is On one hand, you have a kind of software which is discrete, and you have slightly more complex hardware and even more complex physical systems. So you need to think about code design of all these things. So even though you might be studying individual disciplines, finally when you are designing a system like automotive or aerospace, all the disciplines, all the engineers need to come together, right, and work together to build a product. If these different disciplines, people have to come together and then work together, it would be desirable to have a single framework for describing things, right? Finally, the end product might be composed of multiple components from different disciplines, but the starting point should be common, right? The requirements should be in a kind of form that could be understood, and intermediate designs would also be understood by all the engineers, right? So if you need to have that, I think that is where the modeling, the power of modeling comes in. Model abstracts out the details to which you are going to implement different things, right? Now, imagine having a modeling language that can describe your electric motor as well as describe your software that is controlling the power output of an electric motor. Right. Right. Now just to illustrate that how the hardware development is different from software. Now you started from transistor level, gate level, then functional block designs, high level design and synthesis, hardware description languages like VHDL, Verilog. Right now, forerunner for model-based development. Now, if you think of VHDL, Verilog, now people are talking about even System C, right? Forerunner for model-based development. Now, you need to have requirements capturing, modeling, and analysis. Right? In the case of hardware, even it's even more easier to see why we need to have abstract descriptions, which are as flexible as software. Redesign is easy. Right? Control systems development, if you see that it's much older than software and hardware. Rich and extensive literature. Even in the case of analog days, control systems were there. Control objectives and performance. Right? People are stating feedback, feed forward, supervisory controllers, linear and non-linear controllers, and strong mathematical basis was there. Right? Differential equations and so on. So your description mechanism need to accommodate these differential equations also. Right? Now, I think you might recall as part of your this course, you might have studied these hybrid systems as a state machine with differential equations and so on. The reason for this is that, that the end system will have these control systems which are traditionally described using differential equations. So if you look at the classical design methodology, so you start with requirements, analysis of the requirements, design, implementation, and then testing. And then these steps could be iterated, right? Because you might find some bugs in the testing, and then that bugs could be due to requirements, or could be design or implementation. Right? So this is something that your software engineering course, if you are done, this might have been emphasized. Right? This is with respect to software, right? If you look at this, the various steps that I talked about, all the steps except the implementations are informal, as I had talked about. The final object is very formal. It has a definite syntax, semantics, and often need to have deterministic behavior. Whereas all the other steps like design or requirements, people have been using informal notations. Processes and objects not well defined or ambiguous. Now, from one group of people to another group of people, they might use their informal diagrams, informal understandings, and so on. Design and requirement artifacts not precisely defined. When you don't define something precisely, inconsistencies can come in, incompleteness can definitely occur. No clear relationship between different stages. right? So you might have design might be hinting at something, but your implementation might be fulfilling some other requirements. There could be discrepancies, and subjectivity comes in. There is no universal validity. The quality is not uniform, right? When you're developing something today, you might get one output, but 1 week down the line or 1 month down the line, or designs and implementations that you take from off the shelf, 5 years before, if you had designed it, it could have, by looking at the design document, you might get a different understanding. So the reuse could also not be possible sometimes. Right. So I think if you look at the classical methodology, which emphasized only the final phase of coding or system development as important, and less emphasis on the earlier phases, are inadequate for complex systems. There are reviews required for early bug removal. Bugs are often revealed late while testing. Traceability to design steps is not possible. Debugging is also difficult and heavy redesign cost. So not recommended for high integrity systems like the ones that I talked about, like now your pacemaker or automotive or aerospace. So we need a kind of formal methodology, a methodology using precisely defined artifacts at all stages, precise statement of requirements, formal design artifacts. That's what I refer to as models. When we talk about formal, it needs to have a precise syntax and semantics, and there should be a methodology for translating these design models into implementation. Right? That's what we call as model-based development. Models are abstract and high-level descriptions of design objects. Focus on one aspect at a time. Less development and redesign time. Right? There is a kind of flexibility with respect to models. Is that you can easily create models, and then you can redesign them if they are not satisfactory. So it's easy to redesign, redevelop, evaluate. Implementation constraints can be easily placed on those models. You can do what I called as design exploration, design evaluation, and quick prototyping is possible. Right? Now you will later on see that there are modeling environments that are available which allow you to develop models, do some quick evaluations, and then get some kind of performance metrics, and then enables you to debug or refine or revise your models. Right? So the models are physical components. Models of physical components are required for early validation. But this is why now you've got into a kind of new paradigm. Right? In the model-based world, people often talk about simulation. Right? Simulation is becoming very important. Right? More and more important with complex systems that we are talking about. Right? So that simulation is essentially executing the model. Right? So the models need not be purely mathematical models which have a kind of precise syntax and semantics. This model should be executable so that people get a feel of running this. Now, this is what is happening today in, say, for example, in vehicle software development. You build models in a language called Simulink Stateflow, right? Or you could be, if you talk about AI-enabled systems, there could be also some kind of AI platforms that are being used. You build your models, integrate with the rest of the systems, and then run them on a simulation platform, right? You can have the vehicles controlling the vehicle software controlling a vehicle which is there on a kind of video screen, and then there is a road elements are there, other objects are there, and then you can see that supposing that you have developed a new algorithm for a feature like say cruise control. Now you can see its performance by actually running that software on a simulation platform and then seeing that how the vehicle is behaving, how the vehicle is being controlled and so on. So simulation becomes very important. they can be rigorously validated also. If they have a precise syntax, you can translate them into formal models and then do formal verification. And the models can be debugged and revised. And the interesting thing about executable models is that they can be also automatically translated into final code. So that's a kind of traceability between final code and your modeling element. And there's a traceability between models and the requirements. So essentially, the model-based development has given rise to this paradigm of model, verify or simulate, debug, and then keep redesigning the model. And then once you are satisfied with the model, you can automatically generate code. Right, so this is a kind of revision that you're going to get with model-based methodology, that you are going to have a design step becomes more important. Designs are being captured in a high-level modeling language. So just give me a minute. Right. Okay, so the traditional, so in order to explain this model-based development, so you have, this is the final system that you're going to look at. So on the left-hand side, you have a kind of plant. Now that the plant, you can imagine the plant to be as simple as a chamber that is being heated, or it could be your actual, heart, beating heart, a physical system as physical as physiological system, or it could be your automotive vehicle, or it could be your aircraft. And the controller is the one which is being implemented in hardware and software. There is an interaction between them. This is the final system that you're going to see in a schematic diagram. With a kind of model-based development, what you're going to see is, you're going to create a model of the plant, right? I think for CPS, model of the plant also becomes important, right? What is the reason for model of the plant? Because when you're going to do the validation, you're not going to do the validation on a real plant, right? Imagine a pacemaker. So you're not going to say that in order to do validation of your pacemaker, you would like you would request a patient to be there and act as validation platform, right? So the real system cannot be the kind of validation platform. So you need to have the model of that the platform. So that is where the plant model also becomes important. Controller model, right? Now, even the controller, we said that now we are going to build in a kind of using the models. So have a version of the controller in the form of models, and then that controller model is controlling the plant model, so that you can see its behavior, and even the linkages. How the controller is connected to the plant. What are the interfaces that you have? So you will have link models, right? The reason I put this picture is that you see model everywhere on the top layer. So essentially, you need to have build models, and models of the plant, models of the controller, models of their interactions, and then develop everything at the modeling stage, validate, debug, and once you are satisfied that your controller model is controlling, right, in the desired manner, it's meeting all your functional requirements as well as performance requirements, then you can take the controller model and then generate code. Once you're satisfied, you can automatically generate code, and there is a requirement, or there is an expectation that, right, in the model-based development, is that whatever the behavior that you are expecting on the real controller at the bottom, right, that is is faithful to the model that you have developed, right? What you are going to validate, verify is the model, but finally the code is going to run, right? The code is being generated. So you need to ensure that the code generation is faithful in capturing the behavior of the controller model. right? So this also gives rise to a lot of verification and validation problem, right? The verification problem is that whether your controller model satisfies all the requirements that you started with. No, that is one kind of verification problem. The other kind of verification or validation problem is that the controller, the real controller that you are generating out of your code generator, right, using the controller model, is faithful to the controller model. So essentially, this gives rise to what is known as code generator correctness, translator validation, as they are also called. The link models are also faithful to the actual links. The plant model also need to be faithful to the plants. So today, if you see that in a kind of automotive system development, people do this model-based development. Now, a lot of time and efforts. Entire individual departments are there to build plant models to ensure. Now, when you're doing a controller for controlling an engine or controlling an electric motor, not only the software and the hardware team for developing the controllers are there, there are teams who actually go and develop plant models of the electric motors, models of the IC engines. They have to build. There are modeling paradigms. There are modeling tools, and these models are being maintained and then revised and refined because during the early stages of the development, now people build their controller model, and this controller model will interact with this plant model. So that the entire behavior of the ultimate controller is being derived from observing the controller model, how it interacts with the plant model. Right, a lot of time and effort is being spent. This is also called in the automotive and other literatures as hardware in the loop. Right, the hardware that they are talking about is essentially the hardware includes not only the hardware that is implementing the control software, but also the plant models, right, in the engine controller model or the electric motor model and so on. And if you are talking about people in the loop, you need to even build people in the loop, right? Model of the people in the loop, right? You may include the people directly, or you could also have models for people, right? Given this particular response, how the people will react to, right? So human body modeling, human mind modeling, all those things need to be done so that the entire thing of development, now you could do it early in the design phase purely using model. And then once you're satisfied that your models are correct, then you can go and translate them into actual implementation. And there are so various tools. Since all these things are being done in software, various tools supporting such methodologies, commercial and academic tools. So you have, in the case of hardware software code design, I think at some point of time, people are using Metropolis, which came from University of California, Berkeley, spec charts, StateMates at some point of time. These were 10 or 15 years old tools. They have been given rise to a lot of new tools like Simulink State Flow, which is being often used for control system developments, MathWorks, SCADE, Estrel. These are some of the tools. SCADE is, for example, being used in the aerospace industry, whereas Simulink State Flow is quite common in automotive industry. Okay, so I think I have talked for nearly 1 hour. So I would like to give a kind of brief break, some 5 minutes break. I don't know, people, Dr. Behra, if you are there, if there are any questions, this might be a time for some people to ask. Feel free to invite questions, and then I can answer them before going to the next part of the talk.
Okay, sir. So participants, if you have any questions, you can ask.
So you can put it on the chat box also.
Yes.
I'll be back briefly. right? Somebody is calling me. I'll just attend to that call.
Yes, sir. Yes, sir.
All right.
So, sir, I think there is no question till now.
Yeah, I was busy with something else. Today I'm another 1 hour I'm busy. After that I will do it. Okay? Okay? And there's nothing else, right? There's no issue, right? I want to make sure. Okay, okay. Okay. Thank you. Anything people are asking any questions or people are
Sir, there is a question. How
Yeah.
testing can be performed in model-based system?
Oh, I see. Okay, so I think that's a good question. So I think that is why I was talking about simulation, right? In the model-based, can you hear me well?
Yes, sir. Yes, sir. Yes,
Yeah,
sir.
yes. Okay. Right. I think testing is performed on the model, right? So that is also called as simulation. So you build your model from your requirements. You have model of the controller, model of the hardware, and you also have the model of the plant. All of them are in software, right? They what they call as software in loop testing. SIL. No, so this area they call it SIL, software in the loop testing. So you can perform. Some people call it simulation. Right? Extensive efforts are spent in the industry doing this testing early in the design stage. No, you can do testing only because you have precise descriptions. No, in the traditional one, if your designs are in textual documents, you cannot do anything with the textual documents. You can do some kind of informal analysis, right? 5 people sit together and then check that whether the design is correct or not, right? You don't want to have the subjectivity. You can go and actually design test cases at the modeling level, and then you can run. So some of the modeling languages that I talked about, all these modeling languages like SCADE and Simulink Stateflow, they have a whole testing framework. They help you develop test cases, test scripts. You can run those test scripts on the model and then test the result, right? If there are any issues, you can go and correct them and so on. Does that answer?
Sir, this was a chat box question.
Okay.
Sir, so I have a question that in theoretical, how much there is a difference between correctness and formal verification?
Okay, so formal. Look at the complexity, right, of the system that we are building, right? So as I talked about, when you are talking about formal verification is a mathematical technique, right?
Yes.
It can be performed with clever algorithms on your computer, right? But the real system is out on the board, right? Real system is physical system, right? So finally, the correctness of your system is as good as how good it performs on the field, right? This is crucial for CPS, right? It's a cyber physical system.
Yes, sir.
So formal methods can be applied only to models, right? Whatever that you are going to do, only for models, right? It can be used for, in the place of testing your model, you can go and use formal verification, right? Was there a question or?
I think Priyanka Mitra wants to ask something.
Okay.
Priyanka, you can unmute yourself and
Yes, sir. Yes, sir. I understood. Thank you.
you may write.
She's
You may write.
right. She's breaking.
Yes.
She's breaking. That's it. Let her write. Meanwhile, I will just complete my answer. So formal verification is done on the model. You can do it. In fact, there are formal verification tools which are being used in Simulink state flow, verification of Simulink state flow. Okay, so you develop your Simulink state flow models, write your specification, and then actually go and do formal verification of that. So some of the issues of using formal verifications is that scalability, right? For small systems, it's feasible. For the entire vehicle, for example, now you cannot carry out formal verification, right? Even for small systems, when the number of components increase, now the size of the whole system, the state space increases, right? It becomes exponentially large. I think you might have, some people might have talked about the exploding complexity of formal verification. You have to do state space analysis, and then the state space becomes a product of the states of the components, right? Unless you do sufficient abstraction, you may not be able to scale it up. When you're doing abstractions, you have to make sure that your abstraction reflects the reality, right? Otherwise, your verification, it might happen that your verification succeeds, but the actual system fails, right? These are some of the challenges. We have successfully used formal verification in generating test cases. Now, there is one way of using formal verification is that take models, formulate them as a set of formulas, and then use model checking to generate actually test cases. And these test cases can be applied either during simulation or on the actual field testing.
Okay.
Right?
Okay. So, sir, in CPS, suppose there is a fault, then how to handle that? Means CPS can be fault tolerant, or we have to do some mechanism to get rid of a fault.
Right. And also, imagine, right, if there is a fault, right, the fault could be happening. If it is a design fault, you do the design fault by doing careful verification, careful redesign, and so on.
Yes.
Right? If it is a fault in your hardware, random hardware failures can also happen.
Yes.
Right? So that is why this safety engineering is an independent organization within every such company. The safety organization has to carefully analyze what are all the faults that can occur in the system. Right? Hardware faults. How frequent these faults are. How critical these faults are. Right? They have to analyze all of them, prioritize which faults to be taken care, to be more seriously. Right? See, whatever said and done, you are not going to be 100% perfect. Always there will be some corner cases. Some fault, soft hardware errors could cause catastrophes. You cannot go and design for every fault. Right? So that is why the safety engineering goes and identifies what are all the common faults. Right? And then they have a detection mechanism for that. Now you need to detect that. So which means that essentially fault tolerant system need to be built. You have to detect them and then make sure that how you are going to recover. Right? So imagine that some of the activities of vehicle control systems are being controlling your car or vehicle is being given to the machine, right? If there are any faults, what are you going to do, right? So then this in the design phase, even in the requirement phase, they talk about if I get a fault, this is how the system is supposed to respond, right? Maybe handing over control to the human driver, right? That is one aspect, right? And if you have handover, even the handover can fail, right? You're thinking that you're going to the driver is going to take over control. Maybe that the driver starts sleeping, right? Because most of the function is being done by the automatic system. Then if the driver sleeps, then what happens? Then the control is not being given. So you have to take care of what if the driver doesn't take over the control. Now there has to be a um, there has to be built-in mechanism for the vehicle to gracefully degrade. Right? Typically, there are mechanisms. For example, in the case of automotive, so if the driver is not taking over, slowly the speed of the vehicle will reduce, right? And it will go and change, and then it will go and right. Sometimes it may simply stop wherever it was, right? There was a fault. It tried to give control to the driver. Driver was not taking over. Then it is going to reduce the speed. By reducing the speed, you are going to reduce the intensity of the accident, right? And stopping the vehicle, you are going to stop there. You are going to, and then maybe you put your danger light, so that people will take notice of that, right?
Yes.
So these are kind of mechanisms, not recovery mechanisms. Graceful degradation mechanisms are also built in.
Yes.
Okay, these systems necessarily need to be fault tolerant, but you cannot be. When you talk about faults, you can have single fault, or you could have dual faults. You could have multiple faults and so on. You cannot take care of all the faults in the system. All you need to do is that these are the assumptions that I have. I'm going to assume that these are the kinds of faults that are going to happen in the system, and I'm going to attend to those faults. Right upfront, you declare, right? These faults are going to happen. These are more often. These are more critical. I am taking care of that, so that the human being who is going to operate the system is aware of this. Now, these are the kind of design considerations that have gone into that, and so on. Right.
So, sir, if we are working on a problem on fault tolerance system, and we are assuming that our system will tolerate at most one fault, then is it a good system, or is it acceptable?
Okay, so this is what is done at the kind of requirement stage, right? There is a stakeholder, right? There is a stakeholder and the system developer.
Yeah.
They have to agree upon, right?
Okay.
That is where the requirement phase becomes more and more important. Now, even in the case of fault tolerant, right? So I'm going to consider these are the faults that these are the hazards, right? For example, if we take, see, immediately what comes to my mind is automotive, right? So unintended acceleration. Have you heard of this unintended acceleration? I think that's a feedback.
Just
आमच्या आपण होत आहे आपण बिहे थी
So somebody has to mute, right? Can you hear me now?
yes, sir. Yes.
So one of the, see, for example, unintended acceleration. This is one of the very well-known hazards with respect to vehicles.
Yes, sir.
Unintended acceleration means that even though the driver is not pressing the accelerator pedal, the vehicle is accelerating. This was 10 years before. This was 10 years before or 8 years before. This was one of the issues with a Toyota vehicle, right? So there was an accident, and the driver was saying that the vehicle automatically accelerated. I never gave any acceleration command.
Okay.
Right? It's unintended. So this happened because of the control system, right? Because now no longer you are directly in control, right? Traditional vehicles, you are directly, there is a mechanical linkage between the lever on your leg and the actual engine, right?
Yes.
So you press, then it moves. But today, this is no longer there. Now there is a whole box that is in between. There is a wire that is going in. What happens if the wire breaks, or another connectivity breaks, or something happens to the box? Right? It becomes more and more abstract. Then these kinds of errors are going to happen, right? You can imagine that as a kind of a box with input and output. If the human being gives this input, this is the expected output. In between, there is processing that is being done. There's a correspondence between what input that you're going to give and what output that you're going to produce, right? It should not automatically produce some output, right? In this case, in the case of unintended acceleration, there was a box which started mistaking maybe that particular input differently, and then it started accelerating, right? So these are the kinds of things that people will list down at the time of requirements. You have to make sure that these hazards are not there in the system, right? And accordingly, you are going to build in detection mechanisms, right? Which there's a whole safety organization. If you take aerospace, there is a complete independent verification and validation is being done, right? People design. Now there is an aircraft manufacturer, they manufacture their aircrafts, but they are subjected to an independent regulatory body. They will go and check whether these safety checks are there or not. Right? In the case of automotive, there is an internal organization. This is different from the design team. They will go and check now whether it is safe or not, whether it is roadworthy, whether it is airworthy, and so on. Okay, so hope that answers your question.
Yes, sir. Thank you, sir.
Right. Okay. I think some people tried to ask questions, but they could not. They can probably leave in the chat box, and maybe at the end of the talk, we can again have spent some time on those. Right?
Okay, sir.
So let me share again. Can you see my screen now?
Yes, sir.
Okay. Right, I think this is something I talked about. Models need to be formal, so which means that you need languages for describing. Various languages exist. High-level programming languages are used for some time for, say, our hardware. Now, people used to develop hardware in C, do simulations, and then translate them into VHDL, Verilog, and so on. No? That practice was there for some time. So even higher level programming languages like finite state machines, state charts, spec charts, Estrel, Stateflow, these are some of the high level languages which are very precise and formally described. So you can carry out formal verifications on them. Depending upon the applications, different languages have emerged. Data flow diagrams, Lustre, Signal, Simulink, these are data flow diagrams. Hardware description languages, VHDL, Verilog, Unified Modeling Language, UML in the case of software, and in the case of system engineering, people are talking about SysML, an extension of UML. Right, choice of the languages depend upon the nature of the computations needed. Sequential programming models for standard data processing computations, data flow diagrams for iterative data transformations, state machines for controllers, and hardware description languages for hardware components, right? Modeling languages. So you can talk about plant models. They have their own modeling languages for describing an engine or describing an electric motor and so on. Right. Now, so this is Tom. Now, standard software is a transformational system. So you give an input, it gives output, right? Whereas embedded software is reactive. So which means that it starts at some point. Once you reset and start the system, it is expected to execute forever. So it has an ongoing interrelationships with the rest of the system, keeps receiving inputs, and then produces outputs. right? I think this is something, it has an ongoing continuous relationship, concurrency, at least system and an environment. It is event driven. It's looking for certain events. The reason why I'm highlighting these features is that this is to motivate the kind of languages, language constructs that have come in modeling languages, right? They are event driven. So these languages are event oriented languages. Events at unpredictable times. Environment is the master, right? I think this is another aspect that you need to understand is that so you are controlling an environment. Your controller is as good as how nicely you can control your environment. Environment is the master, not your software. Right? The software, the controller cannot say that, no, I'm busy doing something else. You hang on, you cannot say, right? So when a situation arises where you have to brake the vehicle, the controller has to send the brake command, right? You cannot say that, no, I'm busy with doing something else, right? I'm busy controlling the windows, right? So wait till I come back and then brake the vehicle. Now you cannot do that. Now there has to be priorities. So events can come at unpredictable times. Timely response, hard and soft real time. So many of these modeling languages are real-time languages. They are safety critical. So conventional models are inadequate. Right. So let us take now just to give you a flavor of modeling languages. Let us take finite state machines. Right. This is one of the well-known models you have studied in different contexts. Right. So the reason why this is very well-known, very popular is that it is very intuitive and easy to understand. Pictorial appeal is there, and it can be also made very rigorous. Now, standard model for protocols, controllers, and hardware. So let us take a simple example: 3-bit counter. Right, 3-bit counter is essentially a counter which is counting up to 8. It starts from 0. You give an increment, it's going to go to 1, 2, 3, and so on. So if you want to describe 3-bit counter very precisely, of course, you could have a kind of hardware circuit, or you could write a C code and so on. But the easiest model is the one that I show on the right-hand side. Right? All it has is 8 states. It has an initial state indicated by all the states have some labels. Right? And the labels essentially talk about the value of the counter. Right? It resets to 0 when counter reaches the maximum value. Right? So that's all. Now this you could consider as a precise model or description. Right? Model is nothing but a notation in a specified language, having a precise syntax and a precise meaning or semantics. Right? You can all you can do is that quickly go and draw this diagram, and people who are reading these diagrams, if they have a kind of precise notion of what this diagram means, then you have actually described the controller. Right? It's very easy to describe this. Rather than writing for software, you have to declare your variables, how many variables to be used, what instructions to be used, and so on. Or if you take hardware, then hardware description, then you have to have NAND and 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 OR gates. They have to be interconnected correctly and so on. So those are very detailed, right? So whereas here, all you need to do is that pen and paper where you can draw them, right? There are systems where you can go and draw this diagram, and you can go and do simulations also, right? This is very simplistic, so it looks very easy. But the point that I want to say is that you can describe modeling language is essentially some kind of notation or mechanisms for describing such things. Right? The counter behavior is naturally described by a state machine. States determine the current value of the counter. Transitions model state changes to the event C. Right? C can be thought of as an increment. Right? Initial state determines the initial value of the counter. And of course, there is no final state. Why there is no final state for the state machine? Because it is supposed to describe reactive systems now working forever. Right? So there should not be a final state. Unlike a traditional final state machine model where you have a notion of a final state. Right? So just to drive home the point that it can be precisely defined. Now, this is the notation people have used for describing final state machines. You have a finite number of state names, you have an initial state, you have an edge alphabet, and you have an edge transition function. Right? Given this syntax, a precise semantics can be defined. Right? What are the semantics here? Set of all possible sequences of states and edges. Each sequence starts with an initial state. Every state, edge, state triple are adjacent to states connected by an edge. Given a FSM, finite state mission, you can have a unique set of sequences that can be associated. Now, this is also called as a language accepted by a finite state mission. Right? So one of the reasons for using modeling language is that it has a precise meaning or semantics. In the case of finite state machine, the meaning is essentially the language accepted by a finite state machine. Right? Finite state machine model is abstract. Right? It abstracts out various details. Right? How to read inputs, how often to look for inputs, how to represent states and transitions. Now, all you did was that put some circles and then some names and then edges, right? It focuses on specific aspects, namely the event-oriented aspects. It is easy for analysis, debugging. Now, imagine a finite state machine controller involving hundreds of states, right? If you write it in programming language, it will be very huge, right? Whereas in a state machine, you can write it and you can do analysis on that. Redesign cost is reduced, right? You can quickly go and redesign your state machine. And you can have different possible implementations, right? This is also another aspect of modeling language. If you write in abstract description, it can be concretized in different manifestations, right? You can have hardware or software, useful for co-design of systems. Finite state machines have been used for hardware design as well as for software design. And on top, they are intuitive, right? Finite state machine models are intuitive, visual, fewer primitives, easy to learn, less scope for mistakes and confusion, neutral, right? And hence universal applicability for software, hardware, and control engineers. All of them are used to that. They have been taught in their undergraduate curriculum, so it's very easy to teach them. They are also rigorous, right? They're precise and unambiguous, have a rigorous semantics. They can be executed actually, right? Execution mechanism is very simple. An iterative scheme, start with the initial state and then keep iterating over the different states. You wait on a given state, look for an input. Input is of only one kind. And depending upon the input, you just take the action, right? I gave a very simplistic mission, where from one state, there is only one next state. You can imagine them from a given state, there could be multiple states. Depending upon the input, you can go and take one transition or the other transition, right? FSM models code generation. See, what I'm trying to explain using this simple example is that how a notation like finite state machine highlights or explains the various aspects of modeling languages, right? Code generation. FSM models can be refined to different implementations, both hardware and software implementations, right? It's very well known problem, right? 25 years before or 30 years before, now people started using finite state machines and generated hardware, right? Today's hardware synthesis mechanisms or tools people use in the industry are nobody goes and designs now controllers in hardware using gates and so on. Now all they do is that describe in a high-level language like VHDL or Verilog, which have features for describing finite state machines. All right, it was a very well-known initial exercise that you do in hardware design course, how to take a finite state machine and then how efficiently you can translate them into a hardware circuit. You can easily go and implement software, right? So automatic code generation is possible, and it is preferable over hand-generated code, right? Imagine developing a finite state machine. You are going to have less error and the translation is going to translate in an efficient manner. Now, the same translator, if you are going to use using hardware synthesis tool, you are going to generate the same kind of code. So the quality is high and uniform, right? It is like you can think of this as a kind of high-level language, right? And now imagine that now people are writing. When I started my studies, undergraduate studies, people are writing programs in low-level assembly code, right? And slowly they thought that then the value of writing it in a higher level language like Fortran and so on. Right? You can imagine that the same thing is happening in the embedded systems. People are initially in the initial days of embedded systems, people are writing in assembly code. But today nobody writes in assembly code. Everybody writes in Simulink state flow. And powerful code generators are there to generate code to the whatever embedded controller that you are going to employ. This way you can ensure quality. Right? I think many flavors of state machines, edge labeled, mealy machines, state labeled, crypt case structures, which you might have heard of in the context of model checking, state and edge labeled Moore machines, and the labels can be Boolean combinations of inputs and signals. You can go and slowly complicate them, make it complex so that it is reasonably high level language where you can go and encode your computations. You could have even communicating state machines, right? You can have multiple state machines that are communicating over channels and so on. Right, here is another example, right? A traffic light controller. This is again a very, very initial exercise in the hardware design course, right? You can, so I'm not going into the details of that. I'm going to leave the slides so you can go back and then check that. So this is a controller that I'm going to talk about. But the reason why I'm giving this example is that now compared to this example, the state machine example was very trivial. So you might be thinking that only such trivial descriptions can be coded in state machines, but it can be made into as complex as possible. Right? You can talk about a traffic light controller. Right? A traffic light at the intersection of a highway and a farm road. Farm road senses the signals, green, red, setting signals. These are the symbols. You need to use some notations. So this slide essentially describes the various notations for describing. What kind of, and then you can go and describe this state machine, and this description is going to describe this traffic light controller, which is controlling the traffic on an intersection, right? Underlying each traffic controller, each controller controlling the signaling, and intersection. There is an underlying finite state machine, right? Even though finally it is the hardware and software assembly code is controlling that, there is behavior of the traffic controller can be described using a finite state machine. This description, finite state machine description, is not only useful for analysis. The point that I'm trying to say is that that is being used for design also. You start with that, right? The advantages of starting with such high-level description of this controller is that, right, this is reasonably complex, right? It has some labels, but it can be precisely described so that people who are designing this, they can understand that this can be executed, right? It can be executed so that you can think of various scenarios, right? Now, if you take the kind of controller, traffic light controller, what if there is a vehicle that is there on the highway, and there is also another vehicle in the farm road? Can there be a collision, right? Can the traffic controller show green for both the both types of both the farm road as well as the highway, right? And then both the vehicles will go, and there could be intersections. How do you ensure? How do you state properties of this controller, and then go and verify them, right? Verification could be by running the state machine, or it could be also that this state machine can be converted into some kind of symbolic constraints and then you can state your property, like mutual exclusion property, and then you can go and verify them. Right? It can be used for design, it can be used for verification, it can be also used for generating code. Now, these are the kinds of advantages that you have. So these are interesting exercise. You can go back and then see that based upon the meaning that I have given here, you can go and check that whether this finite state machine indeed has the behavior that is expected of this intersection signal controller. Right? Another example, right? A simple lift controller, 3-floor lift. Lift can be in any floor. SI in floor L, request can come from any floor, say RI. RI is the request from floor I. Lift can be asked to move up or down, right? UJ or up down. So then you can go and describe this using this model, right? S1, S2, S3 stands for the state of the lift, where exactly the lift is there, floor 1 or floor 2 or floor 3, right? Whenever there is a request coming from floor 2, then it goes from floor 1 to floor 2, right? By doing an up action, right? So I think that the reason why I gave this example is to show that how the complexity of the labels now can be increased, right? So here, in both these state machines, you have combinations of signals, right? The earlier simple finite state machine counter, now you had only one signal. You could have multiple signals. You could have inputs followed by outputs, and so on. Right? For example, here, when you are going from state S1 to S2, there is an input that's coming, request input for going to the second floor, R2 is coming in. And as a result, the controller is going to react to that by sending a signal called up, right? Up is, you can think of that as a kind of control signal that is given to the electric motor that is operating the vehicle. Right? And another aspect of models is that models is at a higher level of abstraction. You can describe highly non-deterministic controller, right? Suppose lift is in floor 2, state S2. What is the next state when requests R1 and R3 arrive, right? When you are in S2, you can see when R1 or R3 arrives, this lift controller is can either go to S1 or S3, right? Which means that it can go to either floor 1 or floor 3, right? Which is what often happens. You press the button, but the lift goes somewhere else, right? What is the next state when requests R1 and R3 arrive? It can go to S1 or go to S3, right? This model is non-committal. That means this model is not wrong. It allows both kinds of behaviors, right? I think this is the power of abstraction, right? At one level of detail, you don't want to specify that, right? There might be complex algorithms that might be operating, but you might be designing that algorithm later in your design iteration. Initially, all you are worried about is that whether I have this mechanism of accepting some inputs, requests, and then acting according to the inputs, whether that is working or not, right? It's kind of multifunctional, right? You decompose your problem into multiple problems. And when you're solving one problem, you abstract out the other problem, right? What specific algorithm that you need to use, you can abstract out. This is something that comes from a modeling power of finite state machines. Non-determinism is very powerful, right? It arises out of abstraction. Today, you may not be designing the algorithm, right? How to resolve these two conflicting requests. But today, because the concern is more of switching control, right? Then you worry about that. Later, after 1 week down the line, or there might be some other team which might be responsible for developing this controller. When multiple requests comes, how do I go and resolve, right? Whether I should serve floor number 1 or floor number 3, right? There could be decisions that might be taken later. So maybe that, the floor number 3 is an executive floor. Always you have to give preference to that executive floor. So then you might go and build in this preference into the system. But when you're talking about switching control, you're not talking about that, right? Different functions, you decompose the requirements into multiple functions, and each functions you deal with separately, make sure that those functions are implemented correctly, and put all of them together so that the entire system works correctly, right? This is possible if you employ non-deterministic models like state machines. Right? I think this is what I was talking about. Right? And you can also use multiple modeling paradigm. For control, you use finite state machines. For making decisions, you might be using some AI decision algorithm. So, and then you can go and integrate them together. Multiple models, separation of concerns, independent analysis and debugging, and that is one way of managing complexity. And of course, there should be a way of combining different models. And I think this is another aspect that I wanted to talk about. Right now, people might say that no, I'm used to C. Right now, why so invent so many languages? Why not just go and model in C? Right? If you're going to model, this is a simple exercise that I did. It's not really like C language, but it has the flavor of that. But if you're going to do, for example, model this lift controller, you have to go and write so many statements, so many lines. You have to make a lot of decisions, right? Imagine this, 20 lines of code, even if it is 20 lines, it is more complex. It has more error prone. You have to go and debug them, right? The same kind of debugging you could do at a higher level language. A lot of decisions are not taken. A lot of abstraction abilities are there, so you can go and analyze them, right? And another important aspect is that you cannot go and specify non-determinism in a C-like language, right? Abstract descriptions are often not possible in a programming language, right? Programming languages are supposed to describe deterministic computations, whereas modeling languages allows you to describe non-deterministic ones. So C is not natural for such control applications, right? Events and states everything is modeled as variables. That also shows that poor abstraction. Not natural for event-oriented embedded applications. States are implicit in C, right? Whereas when you're talking about controllers, you always talk in terms of controllers. Finite state controller means you have states in the mind, in your mind, right? Commitment to details at an early stage. And too much of work, right? Imagine writing 1,000 lines of code. That's too much of work. Instead of 5 state machines and so on. And often these designs might be discarded, right? You are going to do simulation. You see that this way of doing things is not practicable, right? Then you don't want to spend time, right? You want to spend less time. You want to spend efficiently your time resource. So then you need to have high-level description languages. Right, so these are simple exercise. No, obviously the answer is no. C cannot be non-deterministic. You can go back and see that what happens when 2 requests to go in different directions arrive at a state. That language, that program would have made a decision, implicit decision, which might not be intended. Right. Another thing is that you need to set your intention clear. Now your requirements clear. What am I trying to describe using this model? I need to describe only that much and not anything more, right? The language should not come and put its own constraint, right? Right, here is yet another controller example, right? Again, to show the complexity, a simple thermostat controller, right? As far as the thermostat is concerned, right, you have a kind of off and on state. Whenever the temperature is, right, below or above, you go and switch your state, right? So here there are multiple aspects that are being described. So in addition to the states and then edge labels, inside the state, I have even put some kind of differential equation, right? T dash stands for rate of change of temperature with respect to time. and K1 and K2 are some constants. Depending upon heating or cooling, you might use appropriate positive or negative values for K1 and K2 so that you are actually modeling the physical system here, right? This is not modeling only the controller, but also the physical system, right? I think I had told you that why you need to model the physical system, because you are going to, when you're building the model, you want to validate with respect to the given physical system. But the physical system, you cannot directly go and plug your controller onto the physical system. So initially you do your design model, controller design, as well as the plant model. So you can think of this differential equation as plant models, right? The plant here is essentially the temperature, one parameter of the plant, namely the chamber that's being heated up, right? So you can describe your plants, you can describe your, using this. What is this state machine? This is essentially a hybrid state machine or hybrid controller. Right? So the kind of things that I try to motivate is that how abstract models like state machines can be made more and more complex so that you can introduce differential equation, you can use edge labeled ones, you can have inputs and outputs so that you can make them as expressive as possible and they are precise. You can analyze them, you can develop complex controllers out of that, and you can go and generate code, right? So essentially they have finite number of states, there is an initial state, no final state, non-determinism, result of abstraction, and they have rigorous semantics. They're easy to simulate and debug, and code can be generated automatically, right? Given that finite state machine description, right? You can, for example, describe those state machines in a tool like Simulink State Flow. State Flow is a language for describing finite state machines. And there are controller. Now all you write is in state machine language notation, and the tool can actually generate code in C, C++, and so on. Of course, this simple illustration of finite state machines, they're not. There are problems. Finite state machines are good for small systems, tens of states. Imagine finite state machines with hundreds and thousands of states, right? Such large descriptions are difficult to understand. They are flat and no structure, inflexible to add additional functionalities. Now you need additional structuring mechanisms. So I'm essentially trying to motivate state flow, for example. The state charts, one of the forerunners of state flow. Now they are extensions of finite state machines to have those features. They retain nice features, pictorial appeal, states and transitions, enriched with two features, hierarchy and concurrency. Right? States are of two kinds, OR state and AND state. An OR state can have a whole state machine inside it. Right? For example, this looks like a counter, so count and counting. So here, the count is a super state or an OR state, which contains two other states called not counting and counting. And there are transitions between them. Right? You are initially in the not counting, as shown by that half edge, and then you can go from not counting to count through a symbol or even call init. Now you are initializing, then you go to counting, and you can end this counter when it goes from counting to not counting, denoted by end. And it can be stopped in between by having a stop signal and not having an end signal. Right? So this is an OR state. At the bottom, there is something called end is written there, right, in a specific notation, which means that you can hide them. Any user of the state machine may not see this internal signal. End is an internal signal. Stop and inits are the external signals, right? And the whole thing is a super state containing two states, right? And when the system, so the reason why it's called OR state is it's actually a XOR state, right? Exclusive OR state. When the system is in the state count, it is either in counting or not counting. It cannot be in both the states. And it will be either not counting or counting. Hence the term OR, right? When count is entered, it will enter not counting. Now, when the count itself is a state, right? You can build further complex state machines involving count. When you are entering count, you are actually entering not counting. Default state. Inner states can be OR states. In fact, UML state machine is also very similar, modeled after this, David Harrell's state charts. Right. Now, when we talk about OR states, we are going to talk about AND state also. So let us do inner state. Right? There is a counting is a state. Now we later on show that now counting could be another state containing further states. For example, right, even going before that, both outer and inner states are active simultaneously. Now there is a notion of concurrency is there. So the system is simultaneously in counting and in one of the states, not counting and counting. Right? The system is in the external count state and also in one of the counting and not counting states. So when the outer state exits, inner states also exit it. Right? It's some kind of priorities for transitions. Yeah, you can also think of it as preemption. Right? You're preempting the internal computation. Right? This way of describing is very economical, right? Every transition from outer state corresponds to many transitions from each of the inner states. So the hierarchy kind of brings in this, this kind of compact description. Edge labels can be complex, as I said. Right, here is an example of an AND state, right? So we saw this counting state. This counting state is actually an AND state. Right, this AND state is denoted by these three compartments, which are labeled as S1, S2, and S3. And each of them has their own state machines, right? Again, C0, C1, B0, B1, A0, A1 are all state machines, right? So when you enter counting, you're actually entering C0. And at the same time, you are also in B0. And at the same time, you are in A0, right? Concurrency, right? So simultaneously, control is in all the three states, C0, B0, and A0. And when you're in this state, if there is a signal called tick comes, tick, you can imagine them as a kind of clock tick. When the tick comes, S3 makes a transition from A0 to A1. None of the other states, S1 and S2, are affected because you don't see that tick signal there. When the system is in the state C0, B0, and A1, if another tick comes, S3 actually goes from A1 to A0 because it has a label tick, right? It goes from A1 to A0. Then I have written tick /LT1. That denotes that when this transition takes place from A1 to A0, it takes in as input tick, but generates output LT1. Okay, so just think of it as local tick 1. So what happens with this local tick 1 actually goes and triggers the state machine S2. Right, you see that S2 is in state B0. This LT1 is there as a label for B0 to B1. So when S3 goes from A1 to A0, S2 actually goes from B0 to B1. So after that, you have these three state machines in the state C0, B1, and A0. When a new tick comes, S3 goes from A0 to A1. Nothing else happens in the rest of the system. And another tick comes from S3 again goes from A1 to A0, but it generates LT1. Note that S2 is in state B1. This LT1 goes and triggers that to go from B1 to B0. When B1 to B0 goes, there is an LT2 that is generated. What happens to LT2? LT2 goes and triggers state S1. So that goes from C0 to C1. Right? Like that, Now all these states, three states are running. State machines are running concurrently, and they take received inputs from the external world, as well as there are internal signals like LT1, LT2, and so on. They get triggered. So simultaneously, many transitions can take place. That's why it's called AND state. This is describing, in some sense, concurrency, right? So and the whole thing is in state counting. When you are in state counting, control resides simultaneously in all the three state machines. Initially, control is in C0, B0, A0. Then execution involves simultaneous transition in all of the state machines. When in states C0, B1, A2, right, I think I have already explained that. Right, again, economy of states. An AND state can be flattened into a single state machine, but it will result in exponential number of states and transitions. AND state is a compact and intuitive representation. Right, what are the three components of the state, right? Okay, can you look at this for some time, and you will imagine how the state transitions are going. Right, initially you were in C0, B0, A0. After a tick, it will go to C0, B0, A1. After that, it will go to C0, B0, A0. C0, B1, A0. Then it will go to C0, B0, A0. Then it will go to C0, B1, A0. Then it will go to Z0, P1, A1, and so on. You know what is happening here? What are those three states? These are essentially the 3-bit counter. Now they are essentially talking about the bits of bit values of the 3 bits. C0, C1 on the leftmost side is the most significant bit, and A0, A1 is essentially the zeros and ones of the least significant bit. Right, so this is essentially describing the 8-bit counter that I had written as a kind of flat state machine there earlier. Right, an AND state can be flattened into a right. I think this is what I said. What are the three components? They represent the behavior of the 3 bits of the counter. S3, the least significant bit, S2, the middle, and the S1. Compare this with a flat monolithic description of counter state machine, which is preferable. The present one is robust, right? Can be redesigned to accommodate additional bits. Now you know that if you want to have 16-bit counter or 32-bit counter, you know how to do, right? You can just go and add additional bit counter, right? So here is the complete machine, and it has become reasonably complex, but there is a logic that is there, underlying logic which you can understand, right? So you have this counting, the entire counting state is now inside counting, inside the state, outer state, or state count. So initially you are in not counting, do an init, you count to count, state count. From count, you simultaneously enter C0, B0, and A0. Then for the ticks, you keep operating. At any point of time, you can interrupt this counter by an end signal or a stop signal. Okay. Right. So this is one kind of extension that you can think about. So you can also think about, let me see, because we are just 5 minutes short of your scheduled time. So I'll just quickly finish this. Right. You can also have communication between them. Right. There is a kind of communication, right? Concurrent components of one state communicate with each other. Taking an edge requires certain events to occur. New signals are generated when an edge is taken. These can trigger further transitions in other components, right? As you have seen that the least significant bit transition affects the middle one, and the middle one the most significant one. So a series of transitions can be taken as a result of one transition triggered by an environment event, right? Environment takes the input. You read from environment, multiple transitions take place, and different kinds of communication primitives. More on this later. Right? Right. You can describe all of them using flat machines a huge number of states and transitions, explosion of states and transitions. The state chart, right? This now what I have shown using and or states is actually captured in a language called state charts. UML has a state chart version. Now, if you are familiar with UML or if you have access to UML tool, you can go back and then look at that. There will be some changes in the semantics, the way in which it operates, but ultimately the idea will, is similar. Right? It is easy to understand. It is robust. Can be simulated. Right? The most important thing is that complex state machines can be developed, and then UML, for example, has an inbuilt mechanism for simulating them. You can give a series of inputs and then see that what is the end state. Right? And this whole state machine can be translated into C code. Right? Even though the execution mechanism is complex, you can do that. And this is what typically people try to do. Write complex controller descriptions using state machines in a language like state charts, UML state charts. There are tools, there are environments which can debug your state chart descriptions, which can also analyze your state charts. These are some simple exercises that you could do and see that just to try to get an understanding. But the overall emphasis here is essentially for you to get a feel for what we mean by high-level descriptions or models, what one means by model execution, and so on. Right? There are various extensions to state charts. You can add code to transitions to states, complex data types and function calls, combining textual programs and state charts. So I talked about UML tools, state flow, MathWorks, sync charts. There's another version of the state machines. StateMate and Rhapsody was there some time ago. Right, for example, let me see what is the best way of stopping, I think. So maybe I will stop here. Okay, Dr. Naira, so I think I will stop here.
Yes, sir.
Yes, sir. There's another 3 minutes and it is already late for you people, I think, on Sunday. So any quick questions at this stage or?
So, participants, if you have any question, you can ask.
Sir, I have a question.
Mhm.
Sir, you told that C language is not an appropriate language as it is not providing any kind of abstraction and states and events can be taken as variable. But if you talk about C++ object-oriented languages like C++, Java, then they are supporting the abstraction feature. Plus, if you take about Python, then even the lines of code are also very less. So can we go
Right.
for both languages? And abstraction is supported in all the three languages, C++, Java, and Python. We
Right.
can also take them as an object like events and states.
Right. Okay. So I think that's a good question. So whenever, to some extent, what you're saying is true. Right. Again, the level of abstraction depends upon what you are comfortable with. Right. So if you take state flow, state machines, the control flow, for example, is completely abstracted out there, right? States are abstracted out.
Yes.
So you don't get this level of abstraction in languages like Python or Java, right? You need to go and describe states as a combination of values of variables, right? How many values will decide that? How many variables to be chosen, right? Those are the considerations that you need to have. Of course, as an individual, once you are experienced in that language, you might build an abstraction. You might be working at one level of abstraction, but you might be simultaneously writing at a lower level language, right? So then you will think that, oh, I see it's very natural for me, right? This is what people are doing, right? When they were writing it in assembly language, so human beings are powerful enough to operate at two different levels of abstraction. They think at one level of abstraction, but they can execute at another level of abstraction. Once you get that, then you can directly write it. right? But in the beginning, you have to create that abstraction. So these languages provide that. And another important thing is that if you make mistakes, right, it's not that human beings are now
Yes.
fallible, right? Now, if you make mistakes, debugging them becomes very difficult, right? So whereas such a powerful high-level abstractions might provide that, right? Event. Now, even the event can be event as an abstraction. You can do that in C and so on. So you have to go and make a lot of decisions at an early stage, right? And you can also build your own abstractions. Now, uh, there are opportunities for building your own modeling languages, right? This is what is called meta modeling. Depending upon your application, people actually go and build meta models, new modeling notations that helps you describe your computations, abstractions. Then have your own specialized modeling languages. This is what people do. Uh, okay, so I don't know. Does that answer your question?
Yes, sir. Yes, sir. Thank you, sir.
Right. Okay.
Okay, so is there any question? Okay, so what languages can be recognized by finite automata? It is asked by Venkataswamy, Mr. Venkataswamy.
Right. So I think your question, and I can see that where it is coming from, because the notion of recognition and so on, you must have learned in uh, right in the discrete structure course or something. So, so what I talked that in theory of computation, people use finite state machines for describing languages, right? Like regular languages and so on. There, the purpose is now for describing computations of certain kinds. Now, finite state machines or regular descriptions, regular languages. In the case of compilers, you do lexical analysis using finite state machines. So whereas the context in which we are talking about here is that we are taking that same mechanism and then enriching them, right? If you don't enrich, if you have only simple labels like what you use in the traditional finite state machines, then they are not very expressive, right? As you saw that, you slowly started making it more and more complex, right? I think at one point I said that now you can actually go and write code in that, right? Your transitions are essentially involving actions. Actions you could go and write even C code, simple C code. The moment you are starting to go complicate this modeling formalisms, then you can go and increase the power of these descriptions, and then you can go and recognize the entire Turing computable languages, right? It can be as powerful as an entire programming language.
Thank you, sir. Thank you very much.
Okay, so I think so there is no more question. So
Okay, good. So nice talking to you. I hope that so they can give you feedback if this is the level at which I should go. I should have asked even 1 hour before. Or is it something that they were looking for, or they are looking for something else? Accordingly, I can make slight changes, some changes to my tomorrow's talk. I think tomorrow we have the talk at the same time.
yes, sir. Yes, sir.
Right. So just get feedback and then feel free to let me know so that I can make some
Okay.
course corrections. Okay.
So I thank you very much for this elaborate explanation of modeling of cyber-physical systems. So I hope it will help the participants to understand the cyber-physical systems closely. So we look forward to have your lecture tomorrow and a very good session like today. So thank you
Okay.
very much.
Thank you. Bye.
Thank you, sir.
How do I unshare? Have I unshared? Yeah. Am I still sharing?
No, sir, no.
Okay. Okay. So okay then. Thank you.
Thank you, sir. साढ़े दस.
Okay,
Okay, dear
participant.
participant,
The link
the link will be
in
available in your chat box within a minute. So kindly
fill the
fill the
feedback
feedback
form.
form.
And
And
tomorrow
tomorrow
there
there will be a
session
session at I
I
think
think 10:30.
10:30, and
Professor
Professor
Mahesh
Mahesh
Chandra
Chandragobil will be
going to
going to
discuss
discuss about the
formal
formal
things.
things.
Okay.
Okay,
And
and
I
I
think
think the
session
session
timing is
timing is
10:30
10:30
onwards.
onwards. So
I
I
hope
hope
you
you
will
will
be
be
available
available
at
at 10:20
10:20
approx.
approx.
Okay,
Thanks
thanks for
for
everyone to
joining.
join here. Okay,
Thank you.
thank you. Have a good day.
बाकी सारे लोग तो पूछ रहे थे कि समझ रहे हो, समझ ये इसको कुछ फर्क नहीं पड़ता, इसको कैसा इसको कुछ फर्क नहीं पड़ता, वो बोलते जा रहे हैं, क्या पूछ रहे हो आप? नहीं ये बोलो बाकी सारे पूछ रहे थे मतलब हो या चले गए क्या? मुझे तो ये डाउट ये भी है, यही था कि और था लग रहा है कि ये लेक्चर लेते हैं। अच्छा लेक्चर देखिए वो मांग रहे हैं। Please provide feedback link for yesterday's evening session. अच्छा हाँ क्यों नहीं आज शायद feedback link for the morning session. बोलो लिख दो कि feedback link will be available after the session here only. लिख दो clearly. Five. Six. Six. Five, six, दोनों देखिए। हाँ वो एक को मांगा था वो कल का शाम को भी कल बताएगा के बाद इसको बंद करो। ओके गुरुदेव का है कल 2 मिनट में यहाँ क्या करें पढ़ना क्या